Hi everyone, I'm Gencer Ersunbul. Welcome to the 10th session of the workshop titled Embedding Geospatial Semantic Data Mining and Data Volume Reduction. Sorry for the problems we had. It was mostly technical problems, so we started a bit late. And plus, we are approaching to the lunch, but don't worry, we are going to listen very great talks related with physically grounded foundation models, AI data compression, neural compression, and more. We have a bit of everything. It's going to be great. So most probably it will pay you off. I don't want to take your time too much, so we can directly start with representation learning for EO, physically plausible foundation models by Jordan Leda from CNES. Whenever you want, you can directly start.
Okay, now? Seems okay. Okay, thank you. So, thank you for coming. So, as the chairman said, I'm Jordan Leda from CNES, the French Space Agency, and I work at CESBio, which is a remote sensing lab in Toulouse. And here are my co-authors. I will present this project, representation learning for Earth observation. But first, I will start by giving the frame on which we are doing this. So when I say this doesn't work, this foundation model is rubbish, etc., I'm saying for this application, our frame. So it's very limited scope. So what we want to do is land surface monitoring with satellites. What does that mean? It means that we want to estimate essential climate and biodiversity variables. So you have a list of the things that we want to estimate from Earth observation data. These are variables that have been defined by the climate and biodiversity communities. And these are the things that they need in order to run carbon cycle models, water cycle models, climate, etc. So we want to monitor all these variables, every point on land surfaces. We are excluding oceans with the resolution up to 10 meters and up to once a week. But we are not trying to provide regular fixed resolutions, or either temporal or spatial. We want to generate maps of these variables with on-demand resolution. And we also want to do forecasting to predict realistic evolutions, but also to generate scenarios by using simulated weather and climate in order to generate scenario evolutions for these variables. Typically, this is how it is done using remote sensing data, using data simulation. That means that we have satellite observations, but the core of the system is built with physical models, which model the processes that we were interested in. These are dynamic models, which are driven by forcing, radiation, precipitation, temperature, etc., starting from initial conditions and some parameters of the systems that we want to model. And these models simulate state variables, soil moisture, temperature, biomass, etc., which is a function of time because we are simulating with forcing. Of course, these variables cannot be directly observed by satellites. So we have observation models which convert these state variables in observables, backscatter coefficient, reflectances, brightness, temperature, etc., which are function of the wavelength on which we observe and also of the time. Again, this is not what the satellite gave us. The satellite gave us observations which are the output of an acquisition model which integrates atmosphere, sensor conditions, sensor characteristics, etc. We simulate all these, we compare with the satellite observations, and then we tune until we reach convergence. And when we reach convergence, we know that we have some set of variables or parameters which corresponds to the reality on the ground. Okay, so this is very costly in terms of computation, and therefore what we want to do is start from satellite observation, is just produce directly these variables here. Okay, so of course foundation models, deep learning, etc., etc. So this is what we are building: a foundation model for land surface monitoring. I wouldn't go into the details. This is a big project funded by academic partners, industrial partners, and the French National Research Agency. Just to say that we have money and we have people, and we hire PhDs and postdocs, so get in touch with me if you are interested. And this is the overview of the system. On the left, you have all the data that we want to ingest, optical, radar, thermal, but also LiDAR, etc. Time series, of course, dense time series, not just one image per season, not just cloud-free images, all acquisitions which are available. And when we want to produce, on the first step, is this joint probabilistic representation, embeddings, okay? But these are not just vectors of features, these are probability distributions of features, because we want to model the uncertainties. Depending on the quantity and the quality of the input data, the same features can be estimated with more or less uncertainty. And this is important for us. So if we stop here, we just have some kind of big foundation model which produces embeddings with the particularity that these are probabilistic embeddings, okay? We won't stop here because we want to generate essential variable maps, okay? So we will put here a decoder, which is a conditional decoder, which will condition on resolution, spatial temporal resolution, but also condition on weather forcing in order to do forecasting and scenario generation. And usually when you train an encoder-decoder architecture, you optimize this with a reconstruction loss or something like this. Of course, we don't have labels for the essential variable maps. And what we do, we go to the first diagram that I showed, and we take the physical models and we put them here. So since these are the variables that we want to estimate, and these are the variables which are driving the physical models, these are the inputs of the physical simulators which reconstruct the input data, okay? And we train this like you would train a typical masked autoencoder or something like this, okay? So the particularity here is that, first of all, we produce embeddings like any foundation model with the particularity that these are probability distributions of the features, not just the features, because we want to propagate the uncertainties in order to generate essential variable maps which are labeled with uncertainties for every pixel of every map. And then the other originality of our approach here is that we put physical models here in order to simulate and train all these by classical mask autoencoding. As I said before, we ingest here time series, and what we do is that we split all data in granules, spatiotemporal granules. That means 10 kilometer by 10 kilometer by 1 week. We gather all the acquisitions in this data cube from all the sensors, and we embed everything in this joint probabilistic representation. And then when we want to generate a map, we just pick the granules which interest us, and we put them on the decoder in order to generate the maps. Okay. Of course, at inference time, we drop the physical simulators, and we are just using either the encodings in order to generate the embeddings, or the encoders and the conditional decoder in order to generate the maps. Okay. So this is not just slideware, even though the project started less than 1 year ago, but we are relying on previous works. I will not go into details, of course, because I don't have time, but we have already done this kind of schema here with optical and time series in order to produce estimations of vegetation variables, and that works rather well. We have other publications on this stuff here. Okay, one thing that we could say is that why not taking an existing foundation model, pre-train or fine-tune, and then just build the decoder? And I will try to explain why. Since the presentation is rather short, I will not go again into the details that we are doing self-supervised learning, multimodal data, really multimodal data, not just RGB plus near infrared or something, or Sentinel-1 plus Sentinel-2. I mean, all the available sensors. And this is important. We want to be able to have a system which, once it's trained, it can use sensors never seen during training. We are starting to see architectures that are able to do this more or less, like DOFA or something like this. We want to go beyond that and really learn physics from the sensors, not just central wavelengths and things like this. Okay, I have already said all this. And really our goal is to help to better estimate these variables, generate maps, not just doing computer vision on Earth observation data, but really help to answer scientific questions related to climate and biodiversity. Okay, what is missing in current works? Okay, when we say multimodal, I'm not talking about text, about videos, about social media and these kind of things. I'm talking about our Earth observation modality and fully exploiting all the dimensions. That means spatial, temporal, that means dense time series, long time stems, several years, and all available wavelengths. Of course, we have plenty of pre-training data, but the existing data sets are not really useful for us because either they lack several spectral bands, they don't use the appropriate levels of correction, they don't exploit the full multitemporality of the data. And also, we want to leverage auxiliary data, weather, climate, topography, and these kind of things. Okay, this is related to the typical variational inference that is done in autoencoders. Our physical magnitudes are not bounded, so they are not Gaussian. They have asymmetric distributions, etc. We have already made some contributions in how to model these latent spaces with different types of distributions. Of course, we are putting physical simulators in the deep learning pipeline, so they have to be fully differential. But also, since the simulator are just models, and as you know, all models are wrong, we have to take into account the errors of these simulators in the training phase. And we have to work also on pre-training strategies because classical things for NLP or computer vision may not work. And we have seen that most of the foundation models that are published are not validated on meaningful downstream tags for our use cases because we need uncertainties, we need to map at high resolution. We can't rely on patch level classification and these kind of things. Of course, some of the generative techniques are not an option for us because we need plausible physics in our systems. Okay, this is I will go into the details. We have made some analysis in terms of the existing data sets and why they are not useful for us, either because they span too short periods, or because they don't fully provide time series but just some selection, or because they filter out cloudy images and we need to exploit all available images. One image which has 80% clouds has 20% useful pixels, so it's a pity not to use them if we want to really monitor timely evolutions of land surfaces. Well, this is just a little bit tongue-in-cheek. RGB is not realistic for us. Saying that some datasets are multimodal because they contain Sentinel-2 level 1C, level 2A, and NDVI, this is not multimodal. This is just one modality, it's Sentinel-2. Okay. Saying that you can describe a spectral band with the central wavelength, it's not accurate enough for our use cases because you have a panchromatic band and a red band which is centered on the same wavelength. You don't have at all the same acquisition. So most models and datasets are doing these assumptions, and we need things like solar angles, sensor angles with accuracy, and these are much more useful than text caption of there's a forest in my image. I mean, we know how to detect forests from images. We have all a spectral bunch. Again, about the evaluation of foundation models, most of them are not evaluated on really meaningful time series tasks for which you need very fine temporal sampling. I don't have the time to go into detail. So as a summary, this is what we want to do. All the essential variables at 10-meter resolution at least once a week, but also on-demand resolution and forecasting. And I stress the fact that we are doing computer vision on Earth observation data. These are other tasks that can be very useful for other applications, not for us. So we need to do plausible physics with accuracies and certainties, etc. The originality of our work is that we include physical models into a variational autoencoder architecture in order to estimate these variables with uncertainties, so fully posterior distributions of the variables. we are going to ingest all available satellites available during training, but even those which will be launched after training. And as I said before, probabilistic representations for uncertainty evaluations are very important for us. And finally, why we are not using existing data sets, we are building a new data sets for our training, and why we are not using existing foundation models because of the different issues that I pointed out previously. They are not enough for our application. So, and just to finish, these are the people who have been working or are right now working on the project, PhD students, postdocs, etc. And as I said before, we have money and we have available positions for postdocs and PhDs, so don't hesitate to get in touch with me. Thank you very much for your attention.
Thanks so much. It was a very interesting talk. Do you have any questions? We have time for one quick question, actually.
Thank you for the talk. It was very interesting. I was wondering, as you said, there is one big problem, which is all your physical models need to be differentiable. And do you have any knowledge of already published works that work on this subject of creating models that are differentiable, or do you have to do it yourself in this project?
No, we have already published things about this. We have, this is not very user-friendly. Okay. So this one here, we've already done this with a radiative transfer model for vegetation, which is called ProCell, which simulates vegetation reflectances and soil reflectances starting from leaf pigments, canopy structure, and these kind of things. It wasn't fully differentiable, so we had to tweak it a little bit, and this is what we plan to do for the other sensors and the other kind of simulators. Yeah, right. But this is a very important point because there are simulators that are very accurate, but they are very heavy in terms of computation. We cannot put this in the training pipeline where you have to do millions of simulations. So we have to find the good trade-off between a model which is realistic enough in terms of physics, but that can run in the training pipeline.
We don't have time because we are already running out of time. Thanks so much. I am hoping that you will be around for the further questions. Let's thank again to the speakers. So there was a change in the program. Now we are moving to the leveraging neural compression for Earth observation data. It will be presented by Isabel Whitman from IBM Research. Floor is yours. Whenever you want, you can start.
I think these might be the old slides. Can you go one to the front? That works. Yeah. Maybe I can quickly check old set of slides. I will on her here.
Seminar. Still got closed. Yep, dollars. Isn't up. Right, again, I was further than it. But no move. We cool yes. It's really awesome. Oh, just look. It's not my table. It'll say sure. It's an English service. There's place. I'm not supposed to. But you know, these children it's tough. Go. Let's say the must. This or something it's gas. Nobody's no isn't fine. But there's this one theater. Do you not say something like fantastic? Sure. And what do you think of it? Well, it's happening. That's the time now. It's a bit of some of their benefits. I'm not saying it's a separate group. Which I well, wait, so this team, that's nice.
Okay, so there's one more change. Let's move on to the next presentation. Parameter efficient adaptation of geospatial foundation models through transport. that will be presented by Valeria Marsocchi from ESA-ESRIN. Sorry for the last minute change.
Hi, everyone. Hi. Okay. These are my slides. Nice. So, okay. Thanks for being here. Today, we're talking about parameter efficient fine-tuning. So basically, again, I will ask you to think about some cool foundation model. Okay. That was the time to think about this foundation model. And they are. No, I just mentioned some of them that are, for example, they're working very well on some tasks. For example, scale MA, cross scale MA. Can you hear me also if I'm not really on the microphone? Also at the end, okay. And is it okay also for people at home?
Actually, it's for virtual attendees, so it's better to speak.
Okay, yeah, okay. It's okay. Okay, it's okay. Okay, great. Thanks. Okay, so I just mentioned three that are kind of successful because of their strategy and because of the results. So for example, scale MA, cross scale MA, and remote clip. But what can this model do? Okay, basically they can work perfectly on a lot of use cases, but if these cases are RGB. And so for example, in this case, it's just a change detection task. What if we have more difficult tasks in which, like this is from Mados, so again, we saw this morning marine debris, for example, segmentation. What if we need more information, like for example, multispectral information? And in some of these also an RGB image can be of help, but in some other like this, it could be even tougher to then segment precisely what we're looking for. So there is a big limitation for this model to work on this because of course they are just pre-trained on RGB bands. To do so, of course, the idea is to fine-tune these models. But how to fine-tune them? So how to put this multispectral information, so spectral information into some models that are already working very well from a spatial point of view. And this was our motivation, basically. So, okay, we took some models that were pre-trained on just RGB images, so one modality. And we wanted really to focus on environmental downstream tasks. So, for example, floods or detection and classification on plumes. But of course, we wanted to avoid end-to-end fine-tuning because, as we know, it's kind of heavy and not all the institutions can afford the computation to end-to-end fine-tune these models because it's an issue not just of memory size, but also on how much much time we need to compute. But our idea is based not on very computer vision and AI, let's say, ideas. So we don't want, for example, to make use of low-rank adaptation or these other techniques, but we want to make use of some priors. So in this case of the package bias that we can find, again, on the data and on the model. So again, on the multispectral images, but also on the model themselves. So for example, in the VITs that we are gonna see to do this in the most effective ways. For this reason, our solution is based on an entangled patch embedding layer and an entangled attention mechanism. And then this is leading to an embedding deflection from which the name deflect is coming, of course. That is deviating the latent trajectory of the embeddings, but still having the same norm displacement, so to save the spatial information that was already learned effectively in our pre-training stage. So let's delve into the methodology. This is the main framework. As I mentioned to you, we have an untangled patch embedder, we have an untangled attention mechanism, and we put all together so that in the end we can, as I told you, deviate, so deflect the trajectory of our embedding, still preserving the norm. If we go into the details of each of them, for example, for the entangled patch embedder, we saw that we divided this in two parts because, as I told you, we wanted, yes, on one end to inject the multispectral information, but we didn't want to destroy what, for example, these good models did. So again, scale ME and so on. So we wanted to extract on the one end the RGB channels and of course this is going to be totally frozen because it's already working well, and we observed from our experience and so on, and not just ours, but every group that is using scale ME can say this. On the other side, and so we are calling this XP, and in which we have the pre-train. But then we are adding XA, in which we found a good way to extract in a very lightweight way this spectral information. How we did it? Basically, we randomly selected some pixel. So again, not caring about the spatial information, but caring about the spectral information. So we selected, for example, a few pixels, and for each pixel, we take all the available bands. And then with this pixel, we completed some statistics. So mean, standard deviation, maximum, quantiles, and so on. And then, of course, depending on how much information we want to filter, we fine-tuned it. Let's say we decided which information to use. Now that we have these two, XP and XA, we are doing an attention mechanism that we call untangled attention mechanism. Why? Because we don't want, again, to break what is already working. And to do this, basically, we are setting the RGB to RGB attention, and we are leaving it frozen, and we're just adding three new neutrino attention that are the self-attention spectral to spectral, and the two cross attention RGB to spectral and spectral for RGB. But we did it not on all the layers or the attention layers of our model, but just on few of them. Of course, this was based on some ablation study that I'll show you later. But basically, again, these big fires are the one in which, of course, we are using these that I showed to you. And that this, what does this lead to? This, of course, is leading to, again, deflecting the direction in the latent space of our embeddings. But still, again, we wanted to in this way separate the cluster that could the latent space in which there could be some overlapping, but still without changing too much the information. And in this case, our not changing too much was to match the original norm. In this case, again, what is working should still be working. Other than that, of course, we had to prove that this makes sense. And the models, the guys that I showed you before. So we selected these three models that are RGB. So they are pre-trained on RGB, so they were perfect for our purpose. And we selected again some datasets that are both classification and segmentation for some environmental applications. So, for example, forest monitoring, marine pollution, and so on. And of course, it's important that they have multispectral information at work. It's just as what I'm saying. Basically, we had some good results. Again, Voltex just focus on what I'm showing you. In average, our model with respect to other methods that are some easier ones, some like norm tuning, bit feed that is just fine-tuning the biases, norm tuning is just fine-tuning the norms. Also, we had lower adaptation. We added also SLR that is shaped for is a scaled lower rank adaptation model that was shaped for remote sensing data. So it was also the best to compare with. In fact, it's the one that is kind of is competitive with our middle. In average, okay, we are doing better, but someone can ask, okay, what about the number of parameters? Also, for the number of parameters, if we compare to the one, again, LoRa and SLR that are working good, that are the most performant, let's say, we have way less parameter. This is also because our method can really be implemented along with other methods. So, for example, in this case, we're showing results in which we're using both deflect and LoRa. So this is a sort of low rank deflect, in which, of course, low rank adaptation is used on attention mechanism again. But we will see that this is we are having better results also when we are not using low ranks. If you want to visualize the results, of course, in average, we are having better results, but then this is also very interesting because we are also comparing to, again, the number of parameters. So, of course, if you have infinite computational power, I'm the first to tell you, okay, let's go and fine-tuning your model because it is way better. But then, among the others, or of course, if you have no power at all, just go with the frozen one. But then, of course, if you're looking for a good threshold, maybe you should at least try deflect. Then, if we want to see some ablation, the one I mentioned to you before, our method can work also on LoRa. So for the main results, we showed this because, of course, it's more convenient to have less parameter but better performances. But also, if you're not using LoRa, and it's this for the three counts, the scale MA, cross scale MA, remote clip, the number of parameters that are that fine-tuned are comparable to the one of SLR, for example. So in that case was 2.5, in this case it's 4%. But the results are, again, they are better also if compared to LoRa in this case. So 51% with respect to LDR and so on. Just for Bariscars and scale MA, this wasn't true, but I mean, in the end, it was okay if we, again, don't know our specific downstream tasks. And then the ablation that we did, it was the one to, here there is an error, sorry, this is about adapted layers. So we tried to adapt different layers. We have tried to adapt just the first, all the layers, or just the Ubernet layers, because the decoder of our encoder is a Ubernet. And we saw that this is working better. And I mean, we are thinking that this is true because in one case we are deflecting too much the embeddings. In the other one, we're not deflecting enough. So trying to have this balance is the best way. So basically at this point, which are the next steps? Of course, the very first next step is to extend this to hyperspectral imagery, because of course it will be of great interest and impact to extend to a very, very higher number of bands. In this case, we pass from 3 to 12, but imagine to pass from 3 to, I don't know, 20, 30, whatever. And then, of course, we are trying also to implement some multi-temporal images, because the final end, of course, is to fill the gap, at least for this niche, let's say, so environmental scientists, to fill the gap with end-to-end fine-tuning. Of course, again, what you have to bring on is that multispectral information and hyperspectral information are very useful, and also thinking of some methods that are not just taken directly from computer vision community or more in general AI community that can work sometime. This, of course, it was possible thanks to my co-authors. One of them is maybe around, the other not, I'm sorry. And that, in the meantime, like always, is thanks.
Thanks so much. Actually, we have quite good time for the questions. If you have any, please feel free. I can give you the microphone.
Thanks. Thanks, Valerio, for this very interesting talk. In the conclusion, you were saying that actually if you deflect on every layer, then it reduces the performance. Could you elaborate this a bit more, because it looks a bit counterintuitive at first?
Our idea is that given that Ubernet is just taking information out of 4 layers out of the all layers of the transformer, deflecting to them was kind of, let's say, leading to changing the norm too much, even when this wasn't useful, basically. So also changing the representation in the pre-training, but these were not being used then to solve the downstream tasks. So this was the idea. Then we didn't really go into details on all of this, but this was our idea, given that this was true for several tasks and several models. So I don't know if this answer, but also for us, it's not totally clear, to be very, very honest. This was just our first idea.
Okay. So maybe it's the deflection approach that is maybe not powerful enough to be able to cope with this change on every layer, but I don't.
Yeah, I mean, we can discuss about it.
Okay, thank you.
Any other question from the audience?
For the so as you say, the best results are obtained when you use a few well-placed deflections. Did you try to apply some network architecture search methods to find the best placement, or did you just try by intuition?
No, because we had to focus on other ablation sites. For example, I didn't mention that we observed that so it's not freelance if you're a person with field, that's it's not. So the short ones did fire fact to elaborate and let's say did some other stuff, like for example, we had to understand also how to align this with this, for example. So we spend, for example, more time in this ablation. Now we're time to go. To go on with other ablation, but for the moment.
Okay, thank you.
Let's thanks to speaker. We can go to the next talk. Okay, then it's time for parameter efficient adaptation of geospatial foundation. Leveraging neural compression for Earth observation data. That will be presented by Isabel Wittmann from IBM Research. So there was a lot of change.
Great, thank you so much. Sorry for adding to the confusion, but still super happy to speak to you guys today now about neural compression for Earth observation data. So I work for IBM Research. As IBM Research, we're also part of the Embed to Scale project that you're going to hear about in the next presentation. And this presentation is focused on our research that we did at IBM. And my main focus for you guys is to understand the main concepts and give you some insights into how compression can show advances for Earth observation. To get started, a quick motivation, although I think most of you are aware. So we're speaking a lot about Earth observation at scale, meaning we have huge data volumes that are already existing, and the rate at which we are collecting data is only increasing. So advances in technology lead to higher resolution, broader coverage, more satellites in space, more data that is being generated every day. A lot of potential for new applications, but also a lot of demands that are being placed on the whole data pipeline. Meaning that throughout the whole data pipeline, from satellite, sending the data to Earth, storing the data, transferring, and then to end users using the data, large volume creates costs and hurdles for people using that data. So already now in reality, there are a lot of prioritization steps that are happening. So there's a downlink bottleneck, not all the data can be sent down. If you guys are running models, you're probably facing the question as well, which years to run it on, which data to use. So all of those are impacts due to the large volume. So how can we reduce the data volume of EO to decrease costs and increase its usability? For that, I want to do a quick background on compression, more particularly on image compression. The general goal of image compression is to retain information, so retain the image, but reduce its intermediate size, meaning that I can store or transfer the same information at a cheaper cost. For this, I want to find a translation of my original input into an intermediate space where it takes up less space. And the main metric we are looking at is the rate. Rate generally represents the amount of storage I need per input symbol. In the case of image, our symbols are pixels. So what we are looking at is the bits per pixel. So for every input pixel, how many bits do I need in the compressed embedding or version of my data? So a quick example, 8-bit RGB image, meaning 3 channels, in its raw format takes up 24 bits per pixel. Core principle that most compression frameworks work with is entropy coding. Entropy coding is a way to find a smart translation from the input to an efficient binary code by using bias in the data. So instead of saying every value of my input, I just save it with the same amount of bits. I want to be smart about which binary representations I choose for my input values. And what I do for that is I look at my whole data set or data source that I want to compress. So we have a couple of samples. And I compute the probability distribution to get an understanding of common pixel values that I'm expecting. And I use this probability distribution to find the mapping from the input to the intermediate space. So let's say the lower numbers here are very common, so I use shorter binary codes for the common numbers. And by that, I leverage the probability of my source to find a variable length encoding that reduces my average storage size across all the input samples. So this really brings advantages if I look at the whole data set. So on average, I have a smaller size. And there's a nice theoretical result based on that that relates entropy to the lower limit of compressibility. So actually, you can use the probability distribution to find the smallest possible size you can compress your source into. So in general, lower entropy, meaning more bias in my data, I can compress more by leveraging that. So this was a theoretical limit for lossless compression, meaning I want to retain all the information. But I can reduce my data size further if I allow some loss. And this brings us to lossy compression. So here I want to reduce the size further by being okay with some loss of information, so-called distortion. So as I want only an approximate reconstruction, I need a measure to give me that loss that was incurred. And in the case of images, the most common measure is peak signal to noise ratio, a measure that is based on the MSE loss. So it's just a pixel-wise loss that tells me how much did my pixel values change when I decompressed, what information did I lose in that sense. And based on that, a high PSNR is good, as it means a low MSE loss. So generally, when I look at compression methods, I have a trade-off here. So always for a given quality level or given distortion level, I try to minimize the rate. Last background slide. What are we looking at later on are RD plots, so rate distortion plots that combine those two metrics. So those are the holy grail of comparing lossy compression methods because they combine both measures. So for example, I have two methods here that for different distortion levels give me the rate. And method A is better in this case, as for the same rate, I get a better reconstruction, or for the same reconstruction, I get a lower rate. And how do most methods do that in practice? And by most methods, I also mean classical codecs like JPEG, what is used throughout image domain worlds. Most methods build on the so-called transform coding scheme. So they divide and conquer this challenge by first applying a transformation to the input before applying a quantization strategy that introduces the loss. So the advantages for this, for example, in the case of JPEG, is that I move from my input domain to the frequency domain, and then I get rid of high frequencies that are less important for the visual perception of humans. So I basically move to a space where it's easier to lose information that I don't care about or that's not so important. And I also want to find a representation that is very efficient for the entropy coding afterwards. So I want to find a independent, nicely biased latent representations to be able to apply entropy coding later on. So in the case of JPEG, the fixed transform would be, for example, moving to the frequency domain. Quantization can be either scalar or vector quantization, although vector quantization is not feasible mostly in reality. And then we put the entropy coding step that we already looked at the slide before. So now moving on to neural, the interesting part. Since a few years ago, neural compressors are popping up, and they work basically the same way. They just leverage learned data representations. So what we're doing here is we replace our fixed transforms with neural networks, for example, CNN backbones, and we estimate the probability model in the latent space. And combining both of that gives us a framework that can be trained end to end. So there are a few tricks that are involved to make this whole pipeline differentiable, but basically it functions similar like a foundation model loss, but we add the rate loss. So we also push the latent size to be compressible. So we have our learned transform. The rate R is estimated throughout the training process by leveraging our theoretical results that connect probability distribution with compressibility. And all of that can be trained with one combined loss for different levels of distortion. So we have a factor like a lambda variable that gives us the trade-off that we want to target. Let's look at some numbers. So when we let's for example look at an RGB Earth observation image. So the input would be 3 channels, 16-bit, 48 bits per pixel. If we apply lossless compression algorithms, we can get up to factor 2 compression. So we can get a bit smaller and retain all of the information. If we're okay with some loss, we in practice often JPEG 2000 or similar methods are being applied, which puts us in the range of 20 to factor 500 compression at different levels of distortion. So to give you an impression, level factor 20 is still okay-ish. You can't really see the effects. Factor somewhere 400, 450, pretty blurry results. You lose a lot of information. If we look at neural methods, we are able to improve upon that rate distortion curves. So those are neural compressors that are being trained on EO data. And if we look at one of the reconstruction, we can see that even though we're still in a very, very low rate scheme, it improves our results. So we can still see more structures and visually better results. So we are able to see some more details. And most neural compressors that are already existing and that are being trained operate somewhere in the scheme of 50 to 500 X compression. And here I used two of the most common frameworks. One was developed 4 years ago, the other one a year later, both by Bawley, very famous author in the field of neural compression. And you can see that the second one is a bit better because it uses a hyperprior in the latent space to further improve the probability model of our data. So what we see here, to summarize, neural compressors can outperform the classical rate distortion codecs. And the improvement is in the range of factor 2. So meaning for the same distortion, we can get half the rate with the neural methods. So how can we further adapt neural compressors to our domain, to Earth observation? We do have a couple of EO domain characteristics. We have more structure, more correlations. How does that reflect in our data? For that, I did an entropy analysis where I looked at the input entropy of individual images to see how complex they are. And as we are comparing normalized or natural images with 8-bit range and EO data with a higher range, I normalized the entropy. And what we can see here is that satellite images have a wider range of entropy values. Meaning in our data sets, we have some images like ocean images with a very low entropy because they don't have so much complexity. Whereas natural images are generally always like a high complexity, a lot of different pixel values, very complex images. So to summarize, EO data sets have a larger spread of input entropy and also lower entropy subclasses. And what that does to our neural compressors, or what can be observed, is that we actually need less dimensions in the latent space. So here we can see an input that is being processed by a neural compressor and the intermediate representation that we get out of this. And as we can see with the EO input, only around a quarter of dimensions is being used. The rest just remains constant. Whereas an ImageNet model needs all of the dimensions and has variability across all of the dimensions. And this is just one sample image, but it holds across the whole data set. So I checked that for the whole data set, these dimensions actually remain invariant. And what we can see here is that the lower entropy of our input actually leads to less dimensions being needed in the latent space. And also the EO models train faster than the general models on natural images. So when we try to classify our characteristics, we have some more input bands, temporal structure, which are all very relevant to compression, but we also have data set wide structures because we can place our images on a global grid and on a global time axis. And the last results I'm going to show you today are targeting whether we can use those data set structures to further improve neural compression for EO. So can we build, for example, specialized models for certain seasons or for certain global locations or geolocations? And one motivation for this is that, for example, here we have two countries, and we see that the input pixel distribution is very different for those. So one is more biased, whereas the other one is more uniform. And the results I found is that generally, general models are really hard to beat. But for some subsets that are very narrow in their input distribution, we can outperform the general models, and they do train fast and perform better and need less dimensions. So the general finding here is that it's hard to beat a general model, but specialized models can work for low entropy subsets that have a very peaky input distribution. And as a last slide, I want to give an outlook, and Thomas is going to pick up on that in the next presentation. EO compression isn't finished with looking at mean square error and looking at an RGB image compression. So the real question here is, how do we prioritize and compress all the available information? And for that, neural compression needs to go beyond MSE losses towards downstream task usability. So how much relevant information is still in my compressed or then decompressed data representation? And how can I leverage all of the available input modalities, input time steps, and get to the underlying information? Because that's what characterizes the domain. It's not like visual images where I want to retain the image. We actually have underlying scientific data that we want to work with. So to summarize, we have a strong need for we're going to wrap up. I will leave this slide here then. But those are our current results that we work towards compression. Thank you.
Thank you so much. Actually, we have time for one quick question, if you have any.
Have you compared the CPU cost for neural compression versus the traditional compression? Does one require more compute or energy?
It's a very good question, very relevant question. I don't have exact numbers for you, but generally the neural compressors are fairly lightweight. So they're just a couple of CNN layers. So the compute cost is on a lower scale than foundation models or something like this. So
Thank you.
Thanks so much.
So hi everyone, I am Begüm Demir from Bifold and TU Berlin. So I will be chairing the last three talks. So now I would like to invite our next speaker, who is Thomas Branchmüller from IBM Research. And he will be talking on embed to scale, transforming Earth observation through AI-driven data compression and collaboration. Yes, stage is yours.
Thank you and welcome. And thank you, Isa, for the introduction. So I can take it from there. And first, I'd like to say kind of Embed to Scale is a European funded project running 3 years. And we have, it's the next slide deck maybe. So I think we swapped the sequence. Yeah. So exactly, and in Embed to Scale, we have many partners here. One is person smiling here from Planet also being part of. Then we have colleagues from the Jülich Supercomputing Center. We have colleagues from German Aerospace Center, from Histesat, University of Zurich, Oxford, and so on. And I'd like to present you our vision. But first, the motivation. Let's see if we run. Okay, good. First, the motivation. So we had a customer requesting 10 years of global flood mapping. So then the question is like, how would you do that if you're not in the possession, if you're not AWS, or where would you run the compute? Would you download the data? Would you run it on your own cluster, etc.? Here is an example. Okay, it would be Sentinel-1 and Sentinel-2. So the data volume would be 22 petabytes per modality. So a lot of data. If you just compute the egress cost, if you download the data from AWS, it would sum up to $8 million. So okay, probably you could get maybe some discount if you would ask. You would spend 520 days downloading time at 10 gigabit per second. On the other hand, the compute using Terramine on a A100, so it still requires 3,000 GPU days, but the cost would be in the range of $300. So it's pretty clear you would do your work on AWS, and I think that's also the business model there. So data gravity persists here. But what would you do now if you have multiple modalities and they are not in the same, they are not in AWS or not on the same data center? Then you basically have to get access to the data. And that's kind of where we want to explore kind of the idea of embeddings, compressed embeddings, to be shared compared to raw data. So, you may have different modalities in data center A. You may not transfer, the raw data products, but you may submit embeddings. And once you receive embeddings in data center C, that's kind of where you would do the analysis. You can run then a decoder head. So this could save you really transfer time as well as egress cost, because that's measured in petabytes. On the other hand, of course, you need less storage. So that's very convenient as well. And I think also we talk about AI kind of saving the planet, and especially in sustainability. But AI can also contribute a lot to electricity consumption. But here, just think about, we could run the AI models or the foundation models once, and then you store the embeddings. And then you just ask multiple times to receive the embeddings. So it also would help kind of, if your data center C, you want to provide a service, you could just run the decoder head. You don't have to run kind of the very expensive encoder. And at the end of the day, as you're storing embeddings, then you could also run similarity searches, etc., to do kind of the data exploration. So are the foundation models there where we need to have them? Looking at the embeddings. So here we explore in the table, like with respect to the input data, what is the data volume of the resulting embedding depending on the model. So here we have Prithvi version 2, 300 million parameters. Oopsie. So there we not even compress. So because we convert kind of the integer values into 32-bit float, we even have a negative compression or below 1. If you look at SSL4EO, the vision transformer there, we already get more than 4x compression. Also the ResNet version, you get something like more than 3. And with Terramine base, we have a factor of 2. But these models were not designed to compress embeddings. Just keep this in mind. So I think that it's really a new opportunity or a new angle we should explore as a community. But the potential is definitely there. So, okay, what's going on? So we within the consortium, we published this lossy neural compression review for especially geospatial data. And we just noticed in the Earth observation domain, kind of the compression topic kicked in fairly late. So 2017, we can see activity is increasing. And as you know, foundation models kicking in 2023. I think also neural compression, what ESA presented in the Earth observation domain, also kicked in only in 2023. So it's a fairly new domain, and I think there's a lot of opportunity for us all here in the room to explore this domain. Right, so within kind of embed to scale, kind of we explored different versions. Okay, ESA presented you before kind of the neural compression, kind of with the entropy encoding pipeline, where we already reached 700x compressions with a 5% performance drop in specific applications. From the Terramine paper, if you read it, you have seen that we are using tokenizers. So these quantized variational autoencoders, there we could demonstrate a 3000x compression improvement, but they are not useful then kind of to do pixel-wise regressions afterwards. So they may be useful if you do image classification, etc. So we have to figure out which method works for which type of application classes. So that's why we set out a challenge at CVPR. So basically the idea was like, okay, let's provide to the community data cubes from Sentinel-1 and Sentinel-2 from the different seasons. And the participants, they should come up with a compressor head. So they should train a compressor head and they should submit to us, the committee, a 1024 dimensional feature vector, which we then in the Jülich Supercomputing Center kind of used to fine-tune different linear heads for 6 downstream tasks to evaluate how good the quality and the generalization of those embeddings was. So here this is again a very large compression rate, and that's kind of we only thought to use image level regression or classification tasks, not pixel-wise applications. So we are happy then to announce kind of the winners of this competition at CVPR, and there's a write-up kind of now about the great results from the different teams. So we had 32 teams participating and 465 submissions. So it's really great kind of to mobilize kind of the community to really spearhead kind of the development of these compressors. So stay tuned. There will be a paper and also the announcement of the winners. But we should move further beyond only compressing individual images, as also ESA started to introduce. We should think about also moving in the direction of video compression using those methods, as we have often multi-temporal applications, in particular, let's say in atmospheric dynamics, but also in the agricultural domain, right? Or we should also leverage kind of the cross-correlation between the different modalities. So if we move into the multimodal domain, and I think that's something we definitely should explore in addition, if it gets to the different applications like biomass monitoring, etc. But yeah, exactly. So that's kind of our trajectory. In addition, as we generate these embeddings, we also tested kind of the search through similarity searches in vector databases. So we generate basically for all the images or for some tiles, we create these embeddings where we can have then a query image to find similar other examples. So we tested this on Big EarthNet, where we had again a query image. Like these were then kind of the corresponding responses where the cosine similarity was very close. Again, also to fit all these embeddings into a vector database can be challenging if you're talking about billion of embeddings. That's kind of why we looked into compression schemes and also what the performance would be. So basically, the float embeddings, they were binarized just to have 0 and 1 values depending on the threshold, or we came up with a 64-bit hash. And on the next slide, you can see that, still, okay, the best performance, as you would expect, and let's say here on the big Elfsnet, with 97% performance, was the float embedding. However, if we binarize them, we get 2x improvement in retrieval speed. So we are somewhere in the range of 20 milliseconds to retrieve images. So some more details can be found in this publication. So these are just some first indications how to use kind of the embeddings in addition kind of to the compression potential. So overall, what I want to mention here is besides reconstructing images, we should think about really using embeddings directly to serve downstream tasks. And it may be that embeddings or specific embeddings can serve specific subsets of tasks. Maybe pixel-wise regressions, compression is not feasible as much as if we're talking about image-level classification. But eventually kind of we can serve all these different topics like definability, inference can be reduced, the transfer, latency as well, or even egress and storage requirements. So we really think, and so that's what we showed with the review paper. So we are just at the start of kind of the new way of exchanging Earth observation data, as we also see with all these announcements from Earth Genome, from Clay, kind of providing embeddings from NIPE, or then also from Major Tom embeddings from Cloudflare and Asteroids. So we just feel it would be great, and that's why in the afternoon there will be a session, I think exactly in this room as well, where we really want to discuss with the community interested in this topic to push kind of the research, what is the state of the union, which embeddings are out there, how are people using them already, then kind of to think about, okay, how can these embeddings really be transformative, what is still missing, and do we need supporting activities? So should we have a group called Earth to VEC with a stronger exchange, maybe also some standardization or alignments of where do we generate embeddings? Should we use the same tile locations, etc.? And then kind of, with this community effort, go forward, meet at different conferences and just make sure that kind of we get the best out of all this technology. So with this, I'd like to invite you, exactly if you want to join after lunch in this room, and thanks for your attention.
Thank you very much. Okay, we have time for a couple of questions.
Thank you for the talk. Yeah, is there any way you can... I don't know if this works. Okay. Is there any way you can control the errors introduced by these sort of compression methods in the embeddings? In the same way you can in JPEG say, okay, I want to remove like these high frequency components. How can you tune what you want to remove or what you want to keep here?
Right. Again, most important is, as we've seen, the rate distortion plots. They give you kind of the menu, how strong you want to compress your data. If you reconstruct, in the case of the foundation models, it would be kind of connecting here, like Pangea or GeoBench, kind of a benchmarking data set to see if with a given compression rate, how well kind of certain downstream tasks would still work. On the other hand, of course, also from a research perspective, we'd like to explore kind of the data embedding space much better. So I think this is something which is ongoing research to really understand how to shape kind of the compressed embeddings to get out the most for specific applications. Yeah.
Thank you.
Yeah.
Any other question?
when you have repeated observation of the same region, if you get the image registration right, I suppose you can get several orders of magnitude more compression. Is that already implemented?
Yeah, that's kind of the next steps. So we already started work in the direction of temporal compression. But as many of us know, right, working with EO data is in that sense not so static, because there's like these clouds and there's the illumination differently, there's the seasonal effect. So I think this will definitely be still a challenge, kind of all these artifacts, how to treat them, how do we deal with clouds, etc., because they're typically not what we want to observe. So these are really topics to be looked into. One could also think about really like pixel-wise, just like looking into the temporal domain, not like taking patches, but really just like embeddings for pixel or really time series data. So there's still a lot of room to explore. Yeah.
Okay, thank you very much again.
Thank you.
So let's move to the next talk that will be given by Lydia Abadi from Another Earth. And she will be talking on synthetic geospatial data for training AI-enabled downstream tasks. Stage start.
So I'm Lydia from Another Earth. So we are working on trying to see the efficiency of using synthetic data and training downstream tasks. So in contrary to what Thomas was talking about, that saving embeddings and using embeddings, and a lot of the research community are using only the embeddings, we are looking on a different perspective for this. So instead of using just the embeddings, where you have to build your model based on that, we are looking into building labeled synthetic data in order to train the architecture for downstream tasks as a whole. So we have done, in regards to that, we have done some experiments, preliminary experiments, and we would like to share the results of these with you. So why are we aiming to use synthetic data as a data augmentation or as a training mechanism for downstream tasks? Mainly because satellite data or remote sensing data are huge, and having them processed or labeled takes a lot of effort. So the training data and the data scarcity conditions is extremely difficult, not on the architecture building side, but on the data set building side. So, and also for some areas, gathering ground truth is not straightforward. So, as a means, maybe using synthetic data that can simulate the ground truth data can be more scalable and help to address these kind of situations and improve downstream task trainings. So our experiments, we aim to generate synthetic data first. So the goal was to train a generative model to learn the spatial and spectral patterns and create the synthetic images, either conditioned on for our downstream task, we chose segmentation. So in that case, our labeled data has to be the land cover mask. And so our generative model have to either be conditioned on a land cover, has to be conditioned on a land cover mask. And then we wanted to also simulate a synthetic land cover labels. So to be able to create our conditional input to be something synthetic, and maybe additionally later on control, adding more control into it, like the distribution of the classes or how much water we need in it. But for now, in our preliminary experiments, we used like the typical word cover lang classes. So for downstream task, we trained segmentation networks. We used UNet, UNet++, DeepLab v3+. The data set we experimented on are the word cover from ESA. They are the 10-meter ground resolution. We took the latest version, the version of 2021 with 11 lang classes. And we trained only on the New York region because we extracted the same subset for NIPE data set, where we didn't train on the whole data set. We only took the New York region area. And our resolution that we use is 512 by 512. the word cover, we use it to train a generative model to generate synthetic land covers that are similar to the word cover ones, and which will eventually be used as an input for the downstream task. While NAIP are also used to generate the conditional generative model. For the generative architectures, for the unconditional generation of the land cover maps, we use latent diffusion with the cross entropy loss, because we want the classes, not the mean squared error loss. We were not interested in reconstruction. While for the conditional generation, for guided, we tried to architecture the spade and the control net, and we wanted to generate optical images that are conditioned on the land covers. So the synthetic land cover we obtained from the latent diffusion, you can see some real samples on the left and a couple of samples on the right of the ones generated by the synthetic model. And here we show some samples of the conditional image generation. On the left, the ones that are generated by spade, given the input masks that are from the word cover and the output RGB images. And similarly, we have the control net conditional generation and the input masks that were given and the output generated by that trained model. So after we have generated synthetic data and synthetic land covers, we now try to use this data to train our segmentation architecture, in that case, our downstream task. And for that, we tried with 3 different networks, UNet, UNet++, DeepLab v3+, and we experimented with different sets of data. So first is the data set that is generated, that is the real RGB images, optical images, with the map coupled with the real land covers, with word cover. The second data set is the optical RGB images generated by control net and conditioned on the real land cover, and then the fake optical images that are generated by the spade network. And the last data set is using the synthetic land cover that we have generated as condition for the optical images that we have generated. So for all of the models, we have trained on 8,000 couples and tested on 2,000 couples, and our evaluation metric is intersection over union. And we tested all models across each other. So for the results of the segmentation models training, so for the first data set, it's kind of like obvious that when we are testing on the same data, we have the best intersection over unions and the best performance. However, we can also notice that testing like the model that's trained on the real data is also generalizing well on the fake data, means that the fake data is able to represent kind of the real data. And also testing on the fake data is able to generalize to be performant also on the real one. Not as good, but here is because we used totally 100% synthetic data and we didn't use it as an augmentation step, which might be more helpful. And we noticed one thing, that for spade, we overfitted because the model was not generating diverse enough inputs. So that generative step is very important to have is able to generate diverse situation of the remote sensing images, or we will end up overfitting, as in this case where it didn't totally generalize to the real or the other models. And also when we didn't use any real data, even the land cover condition was synthetic, we were able to generalize to the real data and the fake data. So as a summary of the results, that we are able to train on fake data and generalize to synthetic data. And also, if they are even conditioned on synthetic data, we are able to we are able to perform also well on the real data. However, as I said before, that we need to be careful with overfitting and the generative model not generating diverse enough data. So the conclusion is we wanted to investigate how other synthetic data can be useful to train downstream tasks. And from the result, it seems so. And maybe as a future direction, we can do data mixing experiments or explore like using it as a data augmentation strategy or fine-tune the generative model for target-specific domains. And also scaling up generation, like instead of just training on a certain amount, certain land cover and optical images, maybe multimodality and different conditioning on the generation phase. Thank you. Do you have
Thank you very much. Okay. Is there any question?
Thank you for the talk. Maybe I missed it. So out of the control net and the spade one, which one did you find to produce better results?
The control net was better because the spade was not able to. The quality of the image itself is okay, but the output is not diverse enough for training a downstream task. Because the goal of the generation phase is to generate images like that can simulate the normal situation, but also very diverse, not uniform across the output. And in the spade case, it was more not diverse.
Okay. Did you also compare the original case and the synthetic generation and then mixing them up together in different ratios?
No, like I compared totally on synthetic and totally on real. I didn't apply it as augmentation or as a mix-up strategy, but it should be done because I think that would lead to the best results.
Sure, thanks.
Okay, so timing, let's move to the last talk. Thank you very much again. So the next talk will be given by Jason Gilman from Element 84, and he will be talking on democratizing Earth observation analytics, the case for systematic distribution of foundation model embeddings by satellite data providers. Now the stage is yours.
Thank you. This is going to be another talk on vector embeddings, and I know I'm the last talk before lunch, so I'll try and make it brief. I'm Jason Gilman with Element 84. My title is too long, but basically what I'm saying is I'm making the case that data providers like ESA and NASA should be creating and distributing their own vector embeddings and indexing them in a catalog, and that will help democratize Earth observation analytics. A little bit of background on me. I'm not from a traditional machine learning background. I've mostly worked on search before and like indexing data like for NASA. Like I was the original developer on NASA's Common Metadata Repository. So we're having a white paper coming on this in the future. Didn't have it done in time. Okay, so Earth observation foundation models are learning the Earth, especially with hyperspectral data. The way that they are being self-supervised learning, they're reflecting the processes and humanity's impact in what they're learning. Everybody here knows what vector embeddings are, but so I probably don't need to go over them. But what I like about them, and I think when people are talking about similarity search, right, we're mentioning that an image of a wheat field in the springtime of a particular health, particular amount of water will have the same embedding of a similar field. And as things get farther apart, like with health of that field, or maybe it's something completely different, the embeddings are farther apart. And this is the feature that really enables their use. This is a image or an animation created by Earth Genome that I really like. And what they did was they took the state of Alabama, divided it up into vector embeddings, and then did clustering on it. And I like how this really shows how different areas cluster together. The coloring is based on the land classification of it. So you can see things like airports and runways and mining and things like that out of this one. I started putting this talk together to convince people like ESA to create vector embeddings before I knew that they actually were already doing that. So I'm excited that they're doing that. I don't know if NASA's doing it to the same extent, but I think this is great. It helps show that, like, hey, I was right. But I don't think that's enough. There's part about this that's putting it into a catalog that I think really enables their use. And so the process for creating vector embeddings, we're taking a source image, we're dividing it up into smaller tiles that are going to be better for closely or more closely related to the feature size that we're actually looking for, creating vector embeddings from those, and then putting them into a data format like Parquet is popular. And this, I think, ends up being where a lot of people stop potentially for distribution or creating it. But I think that this final step here, I think, is important for enabling discovery, which is putting it into a vector database. And what that gives us is an index on vector similarity, so that when a user has a particular area that they're trying to find, they can quickly locate anything that's similar to that across space and time. And they can also limit their query based on space and time as well. So I have been working with Earth Genome as well. So they helped me with my presentation, and they're also helping with the white paper as well. And I'm really appreciative of the work they're doing. So Earth Index, if you go into Earth Index and you're interested in finding things on the ground, you can select individual embeddings here. So what I've selected here, these are horse racing track or for training horses in Florida. And once you've selected that, you've essentially created this labeled set of embeddings that can be then used to find other areas. Some examples that they have, like finding rubber plants in southern Thailand, shrimp farms in the Gulf of Fonseca. And here's a real world example, which I thought was really powerful, which is there was a quarry in the Balkans that was no longer being maintained, and it caused a landslide that killed 19 people. And so Radio Free Europe used Earth Index to find all the quarries in the Balkans, and after that correlated it with licenses and found that about half of them were not licensed, which means they're not being maintained and you don't know the impacts or how they're being run. So I think this is a really powerful example of what happens when we put things like vector embeddings in the hands of people who are not machine learning experts. Putting them in the catalog and giving them the right user interface gives them the ability to go and find out things about the Earth that are impactful. So let's talk about how a user would access the catalog. I've already mentioned, the selecting matches and finding similar. So this is kind of the obvious, easiest first way in. Another way, my clicker isn't working. Another way is if you have a model that maps text to the same embedding space. And so if you have we used a clip model. If you have house with swimming pool, the text, and you map that through the encoder, the same way the image, you'll get an embedding that's very similar as to the actual picture itself. And we built an application that lets users ask in natural language for things like show me new construction within 5 kilometers of the Quabbin Reservoir. And the way this works is we ask the LLM to deconstruct what the user is asking for into component parts. So new construction is used to search the vector database. We use a technique called natural language geocoding to convert within 5 kilometers of the Quabbin Reservoir into a precise polygon. And we can then find exactly what the user is looking for, including limiting by temporal as well. And so what I like about this approach is you have like this very loose ability to specify what you want, but then you can also get the same, this precision as well. If you don't have a model that maps text to the same embedding space, you can also go ahead and pre-label embeddings. And so if you're sort of identifying almost a training set, but in a way it's these labels, which when a user does a search, they can identify a particular set of features that they're looking for. They might be looking for burn scars, drought in particular kinds of areas. And based on the nature of vector embeddings, you can combine them together with different mathematical operations to be able to search for burn scars in alpine areas, for example, or other uses. Change detection is another use case as well. So if we look at vector embeddings for the same location over time, these are from 3 different years. The horizontal axis here represents the dimensions of the vector embedding. The top two are same area in the fall. The vector embeddings are very similar. And then when there's flooding in this last space here, you can see the vector embedding much different. And so if you look at the same place over time, we can immediately tell when something major is happening because the model has learned the semantic content of what's in there. So you can set up change monitoring where you tell it what kind of change you're interested in. As it happens, you can figure out what changes are occurring. Here's a similar example to our other one. We used Sky script on this, and natural language, you can say find forests that have been cleared for houses within 5 miles of a Wachusett reservoir. And what this is doing is we can do a single SQL statement to execute this. And basically the user's saying, essentially, find places which were close to this embedding, that would be forests, but now are closer to a different embedding, houses. And you should see one decline and one increase. And doing that, we can immediately find quickly, like at the speed of like a select statement, the results. If you're used to pixel level change detection, this is so powerful. I think you should be getting an idea right now of the generalizability of a catalog of vector embeddings, right? Instead of it being like a specific fine-tuned purpose, you have this broad set of use cases that it can be used for. Classification, direct model interpretation of embeddings themselves, like having a task-specific head on them. I mentioned change monitoring, or also change summarization, as in, tell me all of the changes that have occurred within 10 miles of Boston in the last 3 years, as an example of something you could go do, and being able to select what are the greatest differences based on the vector similarity in the same location. Building this is not without its challenges and logistics and considerations. So you'd wonder, how much does this cost? Are the benefits realistic and feasible? And like, how do you do it? A lot of the factors come into what are the use cases that you want to enable. Depending on the use case, that impacts what data you choose, like that the sensors have to be able to see something that's actually present in there. And if we look at cost, it breaks down into these 3 categories of ingest, storage, and catalog. Within ingest, where depending on the data size, it's hard to say like the actual end cost that you'll end up with, because it's going to depend on how much tiling you're doing and the tile sizes and how much overlap there is. Earth Index was $6,000, so that was optimized and run on in AWS on like ARM processors. So that gives global coverage with Landsat 2. I think it was a single year, but like a consolidated view of that. So if you're doing Sentinel-2 over a longer period of time, like every single scene, it would end up costing more. The storage of the embeddings themselves relatively cheap. This is put in something like Object Store. Another driver of cost here is the catalog itself. In order to index and make available all those embeddings quickly, you have to put them in a database which can grow in size. So I think it was already mentioned in a talk, right? Like we could go to billions. So we did some calculations based on tile sizes, and we know the number of scenes in Sentinel-2, right? It goes from 25 million to 20 billion embeddings. So with compression, the data should be smaller, but the problem is how many of these embeddings there are. And that's a lot of rows to have in a single database, which is a challenge. And I'd like to see in the future approaches given where we can have these stored in like S3 with a separate index to be able to search them, kind of like how you can do searching on Parquet, which I think technology that doesn't exist yet. So some recommendations to data providers, like identify your ideal use cases, and from that a lot of the other decisions will flow out in terms of the source data, the models. I think everyone should be prototyping and experimenting with this, and not just generating the embeddings, but putting them into a catalog to enable users to do it. And I think more should be done with text-image alignment. And I think there are ways we can still do self-supervised models, but still also have maybe a separate trained model that can generate embeddings in the same space. Thank you.
Is there any question?
Very powerful and motivating pro for embeddings. Thank you. Quick question. I really like the pre-labeled embedding approach. Do you have a notion of how many labeled embeddings you would need to get out something?
I don't. I know from one of the examples from like an Earth genome presentation, they were showing cattle, and it looks different depending on what country you're in, who's running the cattle farm. So I think you could go pretty broadly with this. So I think having some initial ones will set that. Basically, I came up with the idea while I was making the presentation, so I haven't actually tried doing that.
Thanks.
Any other question?
Thanks for the presentation. I was really wondering, you mentioned kind of that you could do this Boolean logic, like plus, minus, and so on, in the sense of we have in the NLP world, there's the queen, minus lady, plus man is the king. Sometimes it works, sometimes it doesn't.
Yeah.
Do you have I haven't seen it in the computer vision world, and also not in the EO world. Have you tried these combinations like, okay, I want to have a flooded area, but in a city, so kind of choosing two images to query the database?
Yeah.
How well does it work?
I don't have metrics on it. I have tried it before, and I did find going with the pure embedding before addition. So I feel like there's some subtleties probably there and it may be choosing which parts of the dimensions are more important for others or not. So one of my coworkers did do something, I think, where they combined it, and they were able to find where they combined it at different percentages to choose how much farther along. So I forgot about that. I think I should see if he has a blog post up about it, or if we can put one on, because I remember he did do it.
Yeah, it would be cool to see what's possible right now.
Yeah.
Where do we have to go with the embedding space shaping? Yeah. Okay, cool.
Any other question? We have time for very short.
Hi, thank you. It was really interesting. I'm curious if what was the model that you used for the embeddings? You described a lot of interesting examples, but what were the models? Like, how were they trained? Like the image to image or the image to text?
I think I can't remember the one that Earth Genome is using. It escapes my mind, but we were using SkyScript.
SkyScript for the image text.
Yeah, and I think like now I've seen multiple presentations about how there's better ones available now too. Yeah.
Thanks.
Okay, so thank you very much. Interesting talk. So at that talk, we complete the session. I hope you enjoyed. So thank you very much to all the authors and also to you for being with us until the last minute. Yeah, thank you.
Okay, voila. Can people hear us? Okay, that's maybe now cool. All right, good. So we have two mics. Hello everybody joining online. So we have some screen issues here. It's an experimental session. That's what we explained here. The idea is kind of to have here a kickoff about an Earth to Vec community. First, we want to talk about what is the state of the union, which embeddings are out there. Second, where are we aiming at? And then third, should we form a community, and how should this community support the exploration of the embedding? So that's really the intention of today's discussion. Do we have the slides nearly there? You have them? Can you share?
Okay.
Huh? Okay, so I think we're getting there. Yeah, so the rockers is launching. 10, 9, 8, 7, 6. Oh, wow, we're there. Okay, cool. All right, so that's our agenda. Don't look at the timeline, so that's totally messed up now. But it's okay. All right, so... okay, can you click one further? I have to click here. All right. Okay, so, we ask kind of colleagues here kind of to send us some of their embeddings, some information about the embeddings. I don't know, Martin, do you want to say something to this slide?
Okay.
Yeah, just come here. It should be interactive, yeah.
Big answer.
Yeah, just like Excel. And we also have, actually Ali is also on there, right? From
Yeah, but so I need to hold the microphone. Okay, I'm giving Kevin give me. Yes, it is. Okay.
With my next, so my back is on the side. Sir, Sam is missing. Buddy, Sam is missing. You better stick teeth. Yeah.
It's okay. Yeah. Yes. So we recently developed our global embeddings. Is the first global embeddings based on the different computed models, and we decided to calculate them in the. Okay. Thanks, Thomas. We decided to compute these embeddings based in the unified major tom standard grid to have comparable embeddings, also based on the different models to assess the possibilities of use cases for the wider community. All of the embeddings are shared publicly via Hugging Face, and also there is in the CRODIAS and as EO data catalog, so the users can use them also with the satellite data. And all the information also is our ArchiveX technical paper. So you can find these embeddings via Hugging Face, as mentioned before in the CRODIAS. So we also decided to share these embeddings with a lot of rich metadata, so make these embeddings easily findable. Also, and make the users can make some filtering, so check for the specific area regions, also based on the typical time scale. So based on the different models, we have about 40 billions of embeddings which is shared publicly for people. So we are waiting also for people they can use them, and also we were waiting for the community the feedback and also how they use them, and prepare several use cases based on them. Yeah. Okay. There is also another slide. Yeah. Here is the PCA visualization of the embeddings. On above the 15 millions of Sentinel-1 and Sentinel-2 images were processed. Based on that, we selected different models to assess also the different modalities, also the general vision models like Dino, and multimodal like SIGLIP, and also there is a specific Earth observation models, we decided which is the most promising, like SSL4E and MMR, and we share all these data sets, and the scale was about the 40 billion of embeddings, which is ready to use for the people. And later we plan also to share some notebooks, how to use them, and also several use cases. But if you would like to use them, you can also check out them, and we will hope that you will show in your feedback about it. Yeah, so thank you.
Okay, thank you. Thank you, Marcin. Is there a question for Marcin? Yeah, okay. I don't know, do we have some... yeah, we have now cables and cables, yeah. Okay, good.
Okay.
Is there a question? Do we have a mic?
Yeah, I've got a mic now. I was wondering about the temporal and spatial coverage. Is it considered like an entire view of all of Sentinel-2, or is it sort of a smaller subset?
We decided to compute these embeddings based on the major tom data set, which is the random time range. Yeah, so it will be in the mic slides about the major tom, because is the computed once in the acquisition for the whole the globe, but in different for each grid cells of major tom in different time range. Yeah.
What's the, so if it's not all of it and major tom I originally created as like a training data set, what are you expecting as the use cases for the embeddings?
Yes, so firstly we can develop some easily general vision use cases like image-to-image search. Yeah, for example, for SIGLIP model we can also take the text-to-image search, but in the case of the this foundation model like Decure, SSL4E, and MMR, we plan to also use them like for such modelings or classification task. Like for example, we plan to use them for forest type classification, also for maybe some biomass monitoring, maybe. Yeah.
That's fast.
Okay. Yeah, because we split it. Yeah. Okay.
Yeah.
Is it how do you get to it? Is it available in any cloud providers or any?
Yes. Yes, they are available via CrowdDS, which is on all the cloud storage via our data catalog. So via S3 storage, all of the embeddings are available. Yep.
Nice, thank you.
Cool. Maybe one question from my side. So what is the plan forward? Is the idea to go beyond the Major Tom dataset?
Maybe firstly, we would like to assess the potential of the embeddings based on the use cases. So we computed a lot of embeddings. I think that there's the larger embeddings dataset and globally. So we have a lot of data. So we should now more focus on the typical use cases and that. So on.
Cool. Is there a question from online? Just shout out. Okay. If not, thanks a lot, Marcin. If you can, no, I can click here. Okay, cool. All right, then I'm not sure if Uno is here from Clay. Uno, are you there? I don't see him. Exactly. So did anybody work with Clay embeddings so far? So to our knowledge, they have the NIPE data and S1 and S2 and DM. At least partially available. Anybody worked or touched the Clay embeddings? Not yet. Because I think that this would also be maybe a question also before we've seen your presentation and you dealt mainly with high resolution data. How suitable are the embeddings kind of in low resolution settings versus high resolution settings?
I used.
Do you have the mic? Oh. Yeah. Okay. Okay. Cool. Yeah. Mm-hmm.
The examples that I showed where we were doing, and if you didn't see my presentation before, I showed examples where you could do natural language search for features on the ground, like you can find school buses and things, and we used NAPE data to generate embeddings. So I don't have experience using Clay, but one of the things I was wondering about before they created it, I was telling them that if they're going to do from year to year, one of the things is you want the tiles to be the same from year to year. And I don't think they did that, which I think might hurt change detection if the embeddings aren't aligned. But I think they'd be good within a particular year.
Yeah, absolutely. Okay, so that's maybe then a question to Bruno once he shows up in another event. Then exactly kind of the next slide is Earth genome. That's what you were talking about. Exactly. So how did you choose kind of the Earth genome data set? Is that right? So I think it was the SoftCom model, right? And that was
so I'm not from Earth genome. I just know them. And I was inspired by them. And so I am working with them on the white paper that we're writing. So I don't think I can speak to why the particular model was chosen. Hopefully they'd be online to answer these questions, though.
Yeah, great. Yep.
All the. So yeah, just to fill in here. I didn't see the Clay one, but just to into the Clay slide, I'm looking at the Teams meeting, but I do know last time I talked to Bruno, I think they are switching to major alignment on major grid. So the grid issues, I think year over year will be solved. And likewise, we've done the same. So the embeddings we have, they are on. We've been doing lots of evaluation on downstream capability. Basically, speaking the soft versus other models, that's really the focus that we have right now is really trying to pick the best over. Trying to determine what best even means, but the best overall for different downstream applications, and then application development. So that's really the main focus right now. We do have global coverage at 320 meter grid squares a major top grid published on source.coop, and that's for 2024 to 25. We also have a few select AOIs for other years available, and those are all built off the L2 composites that we also published source.coop.
Okay, cool. Thanks, Hutch. Can you say something how people are using the Earth genome?
Yeah, so we've exposed everything through the Earth Index application, which is essentially nearest neighbor search. We're also building in, we're sort of our focus right now is building models on top of that, sort of on the fly, so more exhaustive search. We're using it for everything from this use case is sort of, finding things, and so we don't have we probably have several hundred users. We're getting ready to do a survey on who's using what for all the different use cases. We can sort of peek into the application. We try not to do that too much.
Yeah.
But that, so finding things, but also for different crop coverages things. We have lots of different projects with other people going on, but different types of agricultural coverage, cocoa plantations, for example, things like that. So land coverage. It's unfortunate Ben is on parental leave, so he can't be here, but he'd be able to speak a little bit more. I could talk more about the nuts and bolts of technology.
Any question from the audience for Hutch?
Yeah.
Yeah.
Just a question, is there maybe a way to connect to the users to find out a little bit of statistics of what they are using it for? Is their consent? So to just get a better grip on what I'm thinking in terms of downstream tasks that we want to add for the benchmarking of vulnerabilities. But that would be interesting to see what's the real world use cases. What is it better to find? What is finding out interesting areas would be. So do you think it's a law?
Yeah, we know a lot of the because it is sort of invite at this point, so we know the organizations that we've invited and what they're working on. Lots of indigenous groups in South America, so things like that. Before, just also seeing like deforestation, even in Europe, as being being of interest to people. Well, we do plan. I think in the next couple of weeks we're gonna work on a engagement with our users, try to do some surveys and things to influence not only the embeddings themselves but also the application development going forward.
Yeah, that'd be nice to maybe lead that with our efforts of pushing this general benchmark. What is a good model that we're going to start now?
Yeah, I'd love to know what that means.
Cool, thanks. Right then, the other kind of piece of work and which is out there is from the NASA Earth data similarity search based on MODIS data. Is somebody from NASA here? Okay, I don't see them. Yeah, exactly. So here they used the model, kind of the Sinclair model, contrastive loss. And the platform is still in beta version, but I think they didn't expand beyond MODIS, right? So that's kind of what it is. What's the pre-tree?
The pre-tree is way before.
Yeah, absolutely, right, yeah, exactly. So yeah, no, totally, yeah, exactly. This is there for quite some time, right? Yeah, exactly. I don't know exactly. Do people know about? I think Google also is aiming at. I don't know, making embeddings accessible, maybe on Google Earth Engine. Would you know some specifics about it?
I think it's yearly. I'm already using that model that will not be released.
Oh yeah.
To the best of my knowledge, they're planning to release a yearly, data set of embeddings based on a mosaic, or some other way of combining them per year, and then doing that globally, and then keeping the model closed behind the curtains. That might be just a guess.
Okay, then the embeddings are on Google Earth Engine accessible.
Yeah, I think so. I mean, I think there were a few slides on Geo for Good. About
exactly.
As well.
Exactly. I think, Mate, you also shared some slides from Google, but and there it looked like it's more a temporal embedding. I was not so that was not so clear kind of on.
I think they're also quite interested in interpolating between in space and time. So based on embeddings that you actually compute from raw data, how do you actually go from that to something they call an embedding field quite appropriately, and build a product that is not limited to the acquisitions of the satellite or other sensors.
Yeah. Okay. Right. So are these the major embedding repos out there as of now? Looks like. Okay, cool. Maybe talking again, not everybody was here in the other session. I don't know, Konrad, do you want to, exactly now you're online, do you want to talk about the CBPR challenge? So this is more like a community piece. Exactly, so, sorry, Konrad. Okay, now you can see the slide, yeah.
Yes, okay. Maybe I can summarize this in a couple of sentences. So what we were aiming at is saying that everyone hates that this foundation model generate embeddings that are applicable to all kinds of downstream passengers, and that set up a data challenge that put them to the test to be provided on this necessary within the 1.2 data set that also has been used before here for the embeddings, right? Or we took on platform 4 seasons of Sentinel-1 data. Sentinel-2 has both products, L1C and L3, so that was the correct one and correct account. And so this pile of data generate feature vector then is 1,000 dimensional. So the data reduction it turns out 7K. So then so you reduce the data by 7K. There's no way to do that lossless. So it's a lossy compression. And then in the background, we have a couple of downstream tasks that we then this whole steam regression essentially is regressing percentage or something that the minister and say something first to the official release of these downstream tasks that will have to at the CBPR data challenge along with the announcement, the middle solution, etc. So, and then in the background, the agent was running on the fly to do that linear regression and rank all these solutions. And then we used the ranking to get rid of outliers in the sense of that one of these embeddings worked very well in one task. It doesn't get too much credit, so it's always kept, ranking to the metric that we introduced, the metric, was always relative to others, especially with a couple of baselines to compare to show stuff happens. And with that, this is what happened, and we got very interesting results. So one baseline, for example, was to just average the pixels spatially and temporally to generate an embeddings. The baseline was okay, but was kind of get very quickly by all the other submissions. But we had one solution that didn't score top, but pretty high up in the leaderboard that didn't use either neural methods. It was just PCA was involved there, etc. A couple of tricks, and it performed pretty stable and well. So one impression is also that you really need in more neural compression way, or stay in traditional methods that also work well, and that could maybe on the other end of the spectrum also help to explain a little bit how these embeddings operate and what are these different feature vectors, feature components, feature vectors. So there's this. I also saw the EUR in a trace that performed the code. I still would damn tried to split the embedding space into different buckets that are modality specific or shared among the modalities. But what happens typically is that we have one geospatial scene, and that is recorded by multiple sensors. In opposed to what is one physical scene, there should be some shared knowledge, shared information that focuses on distinct information. For instance, the one which is radar should be more sensitive to any metal structures, which Sentinel-2 is less. So there's also unique feature that you get this one or the other modality, otherwise you one would shoot up another satellite orbit at death or a new piece of information that would correspond. So that's actually what we want to test here. And after we published the GDPR resolution, the entire framework of the code that we want to release, this is an open community effort where people can add more else. This is the reason why I asked earlier, still, can you tell us a little bit the user applications, like what are people interested in, that we can add more doubts in us earlier, sending to storage with us, but we want to add more and more, making kind of an iterative process. So we have the models and see further embeddings work, and everything gets community driven to real world applications. That's a little bit.
Okay, thank you, Konrad. Questions, comments? So maybe, Konrad, one question from my side. I mean, okay, here we were really aggressive, right, with the compression, and then which allows more like image-wise tasks, image-wise regressions, but not pixel-wise. Should we have also competitions going in the direction of having flexibility in the compression, maybe that more like looking at rate distortion or rate performance plots rather than kind of fixed? And then that's one question. And then the other one, do we need yet another benchmarking data set, or can we build on Pangea or GeoBench and so
on? So on the first question, definitely should also go to evaluations beyond compress less, and also reward people if they compress more. Now we could make that the framework is flexible enough to extend to maybe people get the freedom to decide how much they want to compress, and the more they compress, this we factor into the accuracy score, something like that. So definitely yes, I think this is just a starter. I see. We'll present it at CDPR and was on the metric. We introduced a new one, and then we very much hope that people, and this is hopefully the way to kickstart after this meeting today here, to hear from others and to make them positive. It's an effort that one team does, and then people are not interested in walking away because we missed the target. But it really comes together. There's this interest that we can shape it. Yes, definitely. And the second question was,
the benchmarking data set. I mean, in principle, we can build on it.
I would say we start with what we have, and then if we see gaps that we want to need to fill, we extend it. I really want to make it an iterative process. Keep the community involved. Maybe a follow up after that, the meeting, which platform we can use to stay in touch.
Cool. Okay, thanks. Exactly, and here in this competition, the challenge was also a bit kind of we had to train. I mean, people submitted the features, and then kind of this linear projection heads had to be trained. And there, Jülich was kind of setting up kind of a platform to really do this automatically. So I think it's a Kaggle plus competition, let's say. I think that was pretty cool, yeah. Right, exactly. So if we go back, okay, sorry, I have to juggle a bit two devices here. If you go back to the agenda, okay, just like, okay, State of the Union. Okay, so I think we have a bit of an overview, which embeddings are there. We have the I don't know, are there other community activities on embeddings? Now this CVPR challenge was one. Exactly, so like, is there also from Earth Genome or others, do you set out competitions, or exactly, so how do we engage with the community? Or I don't know, also from Cloudflare, well, Marcin, do you have kind of ways kind of to engage with the community? Or the paper, the publications, and
currently we made second release of embeddings. So now we are waiting for the community engagement and monitor which embeddings people use and for which purposes. Yeah, maybe yes.
Yeah. Did you get the slides from Asterisk?
Yeah, sorry.
It was
maybe
uploaded today. Yeah, true.
But now I have a problem.
No worries at all.
I can maybe show you.
Because that's why I was saying earlier that I would cover some slides and some of the answers would be there. I can try to. I mean, the community maybe is. It's one context that was planned to be covered, but I don't want to disrupt the
No,
But
yeah.
if you have the slides,
Actually, let me see if it's there. But then I can only show it on this display because that
Wait a sec.
Oh, can you check if it?
Yes.
Yeah, exactly. Okay, cool.
We maybe share the WebEx. Can I share my screen on the WebEx? And I've shared the WebEx screen here. If you're about to use the WebEx,
just send the embeddings of my slides, please.
So is it a new file or you add it to the CF session? Sorry, I think for the guys on the Teams, they may not see it. Okay, we have to. Yeah.
Sorry, was it?
Okay, what we can do is, but okay, it's blurred probably. Okay, you guys can see the screen now, and then I have to go back there. Okay, that works.
Yeah.
Okay, maybe then in the meantime, maybe it's good. Ah, cool. Okay, good. Right, you can talk here.
Thank you.
Oh, it's going directly from the stream, right?
Yeah.
Oh, like this, you mean? Ah, okay. But is it not mirrored? It looks quite mirrored.
But then it's straight.
If you have some, okay. Can you read this like backwards? Okay, maybe you can set up a lens that.
Scroll up.
It's a nice exercise, I guess. So I'll be covering quite a similar context to Cloudflare, just because we're collaborating on a bunch of projects. So I'm Miko. I'm one of the 3 co-founders. I cannot change the slides. Okay, I will ask in a sec. Can you go back to the first one? I'm Miko. I'm one of the 3 co-founders of Asterisk Labs, and I just wanted to give you like a wider context of like how Major Tom came to be and how it then evolved into something where that also integrates embeddings and what we think is the actual value of that we're providing within the project. So maybe I can go to the first slide, and a quick shout out to Lion.io, which is I think a few weeks project that I started right after joining PhilLab in 2023, which was my first time of playing with the embedding. So this is just a random image from the paper that I pulled down. But what was quite interesting to me is that like so many interesting models like Stable Diffusion or CLIP have been built on top of image and text pairs. And in 2023, we didn't have many datasets that would combine image, satellite images and text. Right now, that has changed, thankfully. But back then, I was just thinking like, okay, does Stable Diffusion have a decent representation of remote sensing data just from the 5 billion of images that it has been trained on from the web? So one way to test for that is to embed the 5 billion images, and thankfully I didn't have to do it myself. It was already done by people responsible for the Lion 5B dataset, but what you can then do is just use the existing vector database of embeddings to filter out your data to see whether you actually get some interesting remote sensing data in Lion 5B. And obviously you do, because people do talk about satellite data online, and this is the main source of Lion 5B. So this just shows you like a nice axis on, I don't know if this, you can kind of tell. And these are basically the 2 dimensions of similarity that we used for filtering. So we have visual similarity. So in the top left, we have a real satellite image from CloudSen 1.2 and a morphology sample that looks quite like it, especially if you look at the original resolutions of the images and not the compressed version. However, they are naturally semantically very dissimilar, and what we could do back then is check for the match, the cosine similarity between these, between the text associated with the image and our anchor image that we used. And this actually nicely leads, and obviously like you have 3 quadrants where you have like both visual and semantic similarity, neither or one, but not the other, right? And back then we used CloudSen 1.2, which was a cloud segmentation dataset, just because there wasn't a lot of free and quick to use pre-computed datasets with Sentinel-2. You would have to just build everything from scratch, which leads me to the next slide. Very soon, can we move? Oh, it's loading, okay.
So this was one of like a very like direct motivation for building Major Tom was that we didn't have this kind of very fast access to our large and fairly uniform sampling of the Copernicus data. So I had to look for some substitutes. I had to look for a cloud-free imagery from a cloud segmentation dataset, which just didn't make sense. So I approached Ali, the other co-creator of Major Tom, and I said, "Hey, I'm really struggling. I cannot build anything like any of the things that I want to build just because the dataset that I'm looking for doesn't exist. Like, why don't we just try to take advantage of being at ESA and build something that covers Copernicus archive quite well?" And that maybe answers the questions like what the context of Major Tom is. Like, why do we have this specific temporal sampling? Why don't we have time series? I mean, what we try to do is just try to get every single piece of Earth from Copernicus program as a sort of like pre-training data set, right? So what we do is we get a uniform random sample from each location of the grid, and we get both Sentinel-1, Sentinel-2. Now we also have the digital elevation model, and there is also an upcoming extension with the land use land cover. And we then look for a place where we can distribute it as easily as possible. And back then, Hugging Face would allow you to upload 50 terabytes of data for free for anyone to use. And that's still available. However, right now, that limit is only 300 gigabytes. So no more Major Toms on Hugging Face. We were quite lucky in 2023. I think that's changed a few months ago. In any case, we have all of this data that allows us to, first of all, do the stuff like self-supervised learning, generative modeling, and so on. And the models built on top of Major Tom just keep popping up in the last couple of months. I'll move on to the next slide, which brings me to a few years later. Oh, still loading. Let's wait a little longer. It's getting there. You can kind of see part of the slide. So I'll start describing that part of the slide. This is the visualization we've made quite recently based on MMEarth model. So this is the biggest expansion we've built with Cloudflare. Cloudflare is the provider for the Copernicus, the cloud provider for the whole Copernicus program. So it's just, oh, this looks amazing. I'm so glad how it turned out. See, that's definitely compressed. If you go to the Major Tom page, you will probably somewhere find the rotating globe with very cool colors. So I really recommend you do that. For now, you have the compressed version embedded to scale. So in any case, back in, I think, September last year, I just thought it would be interesting to do something similar to Major Tom, but in the space of embedding. So like Major Tom is just a way of allowing the users to quickly get up to speed. And like many of models that have recently been released, I was also involved in, and like very often you get the designer is able to download all of like Major Tom data within a few days and just start designing and building the model rather than spending 2 or 3 months on that dataset curation, which often happened in the past whenever I had someone visiting Philip and work with me. Ooh, this is getting better. Amazing. Just because we don't change the slide, we're gaining some quality. I'm glad to see there's a little bit more resolution. In any case, Major Tom Embeddings has a similar approach. So like, why don't we try to not really compress the data, but just reduce the burden of feeding the data through the deep neural networks, right? Like, why don't we just throw it out there, make it as easy as possible for people to play around with and see what happens? So maybe it's not the most responsible approach, but it's the first step that allows people to build on top of the data, right? The same thing that happened with Major Tom, like that. It's not a full solution. The images are nothing unless we do something with them, but we need to provide the same access to the images so that people can randomly do something interesting. So with Cloudflare, we started just computing more and more embeddings because we wanted to provide space for the users to compare different embeddings, see how different modalities play together. And obviously this is something we are experimenting with as well, but our main motivation is to allow the community to build itself as well by just providing the data and seeing what happens. So we have a preprint on the embeddings of Major Tom. It's work in progress. So for now, we've just described how we've done this and what's available. And then the upcoming extension of the preprint will include some of the evaluations. But I really don't believe this will be like the final evaluation or benchmarking of embeddings. This is just like our way of doing some sanity checks and something that's we hope will be quite agnostic. But then we're really excited to see like what happens with the data when it's just lying out there and people can access it. I can't remember what's next. Yeah, maybe we can go to the next one. You can kind of see that there's several data sets. I'll try to answer the previous question as well about the temporal aspect, right? So we have like a random sample per location, like what's the deal with that? So again, like we want to elevate the existing data that's in the major tom dataset and just see what happens when you embed. But that obviously limits the use cases if you want to, for instance, a global sample from 2024, right? What you can still do is just filter your metadata easily and still have a fairly decent coverage globally, right? It's not a full solution, but it's something that allows you to play with things, right? So you can still filter your embeddings and focus on specific spatial temporal regions or anything else, and at least do some preliminary analysis that maybe gives you a little more confidence in acquiring a global data set of Sentinel-2 from 2024, let's say, right? So this is the main purpose, to just like have this fairly low-cost solution that allows you to just make up your mind about what you want to build. I can't remember what the next slide is, but maybe we can see. Oh, amazing. So this is something I'll announce tomorrow. We have this month we will be starting as Asterisk Labs a delivery of an expert report for the ESA Copernicus office that will basically involve a wider vision for the integration of AI into the Copernicus program in the coming years. And part of that will naturally have to do with the embeddings. So we will be carrying out stakeholder and community consultations to just understand a little better how we can not only help the users make use of the data in Copernicus, but also help the designers, the developers, and everyone else to do interesting things, experiment, and build tools that get us maybe even more excited about the Copernicus program. Woo. So right now you can maybe take a photo of our email. If you can just feed it into a good decoder. And if not, you can go to our website, and we are generally very happy to discuss and basically gather your input. So if you have any ideas or questions about how it's going to go forward, we are very, very open. And we will also host probably a few events at the ESA-LPS, Terabytes workshop at ICML, and I think that's about it. I'll also have a quick talk about it tomorrow at the infrastructure session. I think that's me.
So, questions? On my end, going back to this, was it on last year? Did you get any feedback so far on what users are interested in? I heard a couple of where you talk about lossy correction, meaning essentially using information, people get a little bit skeptical and
I would say
just call it pretty shit.
So I didn't hear anything just yet because we're starting probably tomorrow the actual project. So we've just signed a contract today, in fact. But I've heard a lot of complaints at the EGU session about compression, and people not only get skeptical, they get very agitated as well when you mention any type of lossy compression. They were I think the compression session at EGU was the wildest session I've attended during the 5 days of EGU. So I definitely think it's a sensitive topic, and it's interesting to explore for there's always the same question of that keeps popping up about some scientists worrying about the data that gets removed in the lossy compression being completely crucial for testing their hypothesis, right? So it's just interesting to follow the projects like Embed to Scale and other research work. Yeah.
Really wondering if EGU is the right place to ask that question.
Yeah. I didn't ask that question. I was just listening.
It's a super important crowd of stakeholders, right? I mean, I think as researchers, we always want to have the best data as possible, right? But then if you commercialize something and you need to get pragmatic, and then maybe kind of you have to compromise.
I think after you ask that question at EGU, you should immediately leave the room and see what happens through the window.
Thanks for the presentation. Can you
I think this is one thing we have. It's that maybe the audience is more towards the industrial applications where you just can't get around. Of course, whenever you have a research, it's actually very interesting and very that we also discuss in embed to scale with all the use cases and one use cases for clouds and cloud kind of tracking, understanding clouds with University of Oxford, and they essentially say it's fine to use some details on the pixel level, but we want to preserve certain metrics in terms of the cloud, so fractional dimension, etc. So this is something also where a new metrics of the evaluation and benchmarking now for multiple benchmarks, and I see that the pragmatic approach would be the open source the data challenge, that people just add new metrics, good data sets, and then was it a plug and play as we build the code, as Thomas mentioned, right? At Udish, we are running this. It's extendable easily, and then we can analyze all of it.
I think that's like that's like one of the strengths of just like releasing, this data or any other data publicly for free, just because people can quickly make up their mind, like whether this is actually hurting their use case. And at the same time, I think it just makes sense to keep repeating that you might lose a little bit of data or performance, but you just might be able to run your analysis over much wider spatial-temporal context. And sometimes that's much more important to study the dynamics rather than being completely right about every single sample.
Okay, cool. We have Paolo also here. Yeah, in the interest of time. Yep.
Just one question about the embedding data set is single timestamp.
Yeah, it's a single timestamp because it's directly derived from Major Tom.
Yeah.
So what you have to do is, like, if you're interested in a specific date or a month or a year, you just filter out the metadata.
My question is more, do you see this as complementary almost for more models diagnostics, exploration of embedding spaces, all these things, rather than building actual applications?
The Major Tom, I think for me, should always be this sandbox where just people can come and play.
And you see the same.
And then when it comes to like commercializations, building products, that's something that happens outside of Major Tom and is obviously something that is designed internally by various entities. But yeah, I think this is definitely like something that we should all like try to benefit from, because that also allows us to just scope the response of the users before they invest their resources in any of the products in the ecosystem.
Thanks.
Cool. Great. Right. So let me see. So we had a Right. So our goal was to get to the State of the Union. I think we have now a fairly good overview, community activities about embeddings out there, the motivation therefore. So now if we think about how we really would change, if you look at Earth genome and Earth index, so I think there it's really the findability element is interesting. So I guess for you guys, maybe it's like, okay, what will people do with it, right? So I think in the embed to scale, we think in embed to store. Is it useful that you need less storage? Embed to transfer. Is it great that you pay less egress or latency? Then the other one is embed to infer, that you need less inference compute, which can be great. And there in principle, you could also ask like ESA, or Copernicus, how often is certain tiles being downloaded? What is the value if you pre-compute embeddings, and then are they in certain locations 1,000 times downloaded? I think the overall, I think I can't remember, but like I think the overall numbers suggest that maybe the whole data set in Copernicus was downloaded maybe 2 or 3 times, maybe something like this. It's not much, but certain regions would be more. And then the fourth one is the embed to find, right? So I think with Earth genome, they're going in the direction of finding parts. I think also NASA mentioned also they use, I think, the MODI search engine also to compile data sets. I think they had like some annotations, and then they wanted to compile. There was one use case at least. Maybe, do you know more? Sorry?
They use the similarity search to find scenes that have like clouds, and you can go and label them basically. So for curating a data set for labeling. Yeah.
Exactly. So that's the curation of data sets. I think Earth Genome, I think they're also like talking to journalists, right? Kind of identifying areas. And then, exactly, so Mika, you have maybe a comment?
Yeah, I mean, for Major Tom, I think it's just, and the collaboration with Cloudflare, it's mostly about just creating this first step where we have a kind of leveled playing field. And then obviously that can stem in all these directions. It's just that I think the easiest way to get an understanding about, especially the like certain deficiencies and issues with specific models, is to just like let the users experiment a little bit and then see whether like any of these models is good for like finding things. Any of these models is, I mean, it seems like it will always be to some degree domain specific, right? So it's more about like understanding the domains in which specific model can succeed, and then maybe doing more work to compress it, to optimize the data storage, data transfer, to do user-side inference and stuff like that. But first, it's good to get an understanding. Maybe all of these models kind of suck in some way, and we have to just build something completely new in a new way, and maybe that will motivate. Like if all of these models fails in something that's important to the community, that just means we have to do more of the legwork in this very first stage of building the models that actually compute the right representations, because ultimately we're just assessing the representations obtained by the models. So if there's something still missing there, we have to go back and at least improve some parts of that pipeline.
Right. Okay, cool. Right. So, okay, now everybody can invest in this project, Earth2Vec. We have these 4 categories, how the embeddings could really add business value. Okay, each of you can invest now, let's say, $100,000 into either store, transfer, infer, or find. Okay, so let's raise the hand. Okay, sorry guys. Okay, how do we do this now? Okay, we do it with the guys in the room if that's fine with you. Okay, so who would bet 100,000 to embed to store as a business value application? Storage? No? Earth Daily? No? Okay, storage is not an issue. Okay. Who would bet on transfer? Yeah, raise really high. It's 100,000, Okay, so we have about three. Okay, who would bet on the infer? There we have also 3. All right. Okay, now it's getting really interesting. Who is for find? Who would invest in find? Okay, we have maybe something like 9-ish. Okay, so the find element seems to be quite interesting. And then do you think exactly, so if it comes to the resolution, so we see kind of, exactly in the presentation, we were seeing kind of in Earth Genome, we are on S2, Clay has NIPE. If we also interact with text and semantically with kind of the imagery, high resolution may be better. And I don't know, for the low resolution, is there the temporal element important? So are there opinions, like if you go high resolution find, or if you go S2 style find, what are you expecting? Is that the temporal? Yeah, okay.
You didn't ask who wouldn't invest a single dollar.
That's not an option.
Okay, sorry.
Yeah, okay. You wouldn't invest?
No.
Okay, can you say why?
Sorry.
No, that's good. It's good.
No, I mean, I have the feeling that we are doing many things with just Sentinel-1 and Sentinel-2. I'm not talking about very high resolution. I'm talking about lower resolution, longer time spans. And I'm worried that there's going to be a lot of initiatives which do more or less the same with a subset of the wealth of data that we have. And maybe, not stop doing what you're doing, it's great, but maybe also think about all the data archives that we have. There are many applications which need long temporal spans, not just a couple of years, not even just since the launch of the Sentinels. And we also have lower spatial resolution data, but with higher revisit times, which are also useful. And integrating all these data would give embeddings which are much richer, because they include the temporal and larger bands, more spectral bands, etc. So just I'm
Yeah, thanks for this comment. So let's wait. Is that a response?
It's kind of.
Okay, good. Yeah.
So as you say, there are other that
I think that one of the reasons that people have there's lots of
and two is the interoperability of sensors. Like something that some people have mentioned is that for embeddings and foundation models work, you need aligned images. So when you try to use other sensors, those the image that come from those might not be aligned. So how are those embeddings are going to look on the same place on that?
Yeah, I did it. It's calling me. They tell that or information and move position. They.
Yeah, but that's what I mean. But you if you access
buffer and point measure its position in the United States spanning infection.
Okay. Because how do you have positioning if those pixels are not aligned, are not the same?
The available set of just ingredient. I call the position, the date, wavelength, not big, facilities.
Well, my experience is that, I stack some planoscope images and the same pixel is shifted by 2 or 3 pixels and it's not the same. Well, X-ray says it's the same pixels, but it's not. So I'm not sure how, if those are not aligned, you don't have the same tiles over time. I'm not sure how the embedding is.
To you know where the basically
exactly.
So we know it.
Right. Exactly. Let's discuss this afterwards offline. But I think exactly the comment is also great. Let's say in the Embed to Scale project, there's also Philipp Stier from Oxford University, and he's concerned about the next generation weather climate models. So basically, they also have the problem they cannot store the petabytes of data they produce, and they are already kind of in certain areas they compute and statistical representations, and that's what they store. And here you again could do it data-driven compared to feature-driven or handcraft. These are things also exactly we didn't look into as of now that much, but yeah, thanks for the comment. Okay, cool. So let's say with the remaining time, okay, so we have some people investing in our project here. That's great. But now actually, how should we move forward? So do we believe kind of it's great kind of if we get together from time to time? Can this happen through sessions at the conference? Or should we try, I don't know, at LPS or so could be the next occasion kind of to together in something like a more like a brainstorming type of interaction or strong voices, opinions?
What about what they were doing?
Yeah. Okay, so the response was like monthly remote as one thing, right?
What happens?
Yeah. No, absolutely. No, it makes totally sense, right? So maybe we could have like monthly remotes, and then we could have like deep dive sessions. Somebody presents the latest what's going on, and then we could have maybe a focus on maybe some scientific challenges or roadmap discussions. Would people be willing kind of to be organizing?
I would also recommend that like Jessica was Slack show.
Yeah.
But very focused on this stuff.
Yes. Yeah. Exactly. Yeah. Yeah.
Dates.
Exactly, a Slack or Discord channel or something, right? Something like where we could connect easily. Yeah. Could there be a small team we could form to create such hands up? Would be interesting. Cool. Okay, yeah. Okay, I make a photo. Exactly, yeah. How we do it? We can. Yeah. Okay. Exactly.
Could we maybe refrain from creating a new server on Slack or Discord and try to use something that already exists so I don't have one more icon in my Slack or Discord?
Yeah, exactly. What is the best?
I think that's a good question. I don't want to push anything here.
Exactly.
I think there's several Discords and Slacks that would be appropriate. And maybe we could also ask people whether they prefer Discord or Slack, because that's also be a controversial topic. I don't want this to end up like
okay.
you.
Yeah. Right. Exactly. Are they okay? I mean, okay. I think one thing we can do if we find a core team who organizes this monthly meeting, we can define how we want to do this, right? I think let's put it to this. Yeah. Yes. Okay. Sorry. Yeah. Romeo. Yeah. Sorry, I don't see it. Yeah. So, Romeo.
I guess that's also to help organize and these parts of teams.
Yeah. Cool. Exactly. So, those who have my email address, just send me a note. Then we organize ourselves, and for the others, we connect through LinkedIn or something like that. Then we connect. Okay. Right. Exactly. So, what? Exactly. So then we run this. That's a good suggestion. We run this monthly meeting, and maybe at LPS, the sub team can meet there anyway, and then that's how we grow. Any other pressing topics? It's good. Yeah. No it.
Throw them actually.
I said that's now the ETU thing, right? It was like,
I mean, it's more of a thought than a question. It's so we have all these different models, and we are embedding on the same data set from each of them, which is now the exploratory part. That will increase the size of our storage actually compared to data. So let's accept that fact. But I think we need a way to query the embeddings. So we need to come with a community standard or best practice of how we want to catalog our embeddings, because we are going to land in a place in a year probably that we have like 10 different models, globally calculated embeddings stored on a blob storage, and we need to query them. Like the way we query Sentinel-2, Sentinel-1, or a stack basically for embeddings. I'm very curious about that, and my brain is very burning CPU on that. If anyone is interested in that topic, I would like to chat, because I feel we need to come together on a more like software data storage side of things to solve that problem before the flood comes.
Yeah, I think Mate wants to say something. I see it. I can see that you really want.
I just fully agree with that. I see you nodding as well. We should, we should probably join the JET and Radiant Earth with see exactly, on that topic.
Right, and also we have from University of Münster, Jonas is there as well, like working on OpenEO, and Romeo will for sure also like to join. I'm pretty sure. Romeo, sorry, I put you here under the bus, but exactly. No, I mean, definitely, yeah. Okay, yeah, that's it.
Hello, good afternoon, everyone. My name is Kumar. I am part of the NASA Impact team, and I predominantly work on scientific use cases for large language models that involves creating, fine-tuning large downstream applications for large language models and finding ways to use them within the team. And I'm joined by Nicola here, and do you want to introduce yourself?
Well, I'm one of the guys at the ESA Lab, one of the main organizers of this conference. So yeah. and also co-chairing this session because at the ESA Lab we are also funding some project on LLM, agent AI, and stuff like that. So over to you.
Thank you. Let's get started. And today's session is about AI agents, digital assistants, and large language models. And the first topic for the first presentation's topic is leveraging large language models for retrieval augmented generations for enhanced Sentinel-2 data analysis. And it will be presented by Faur from National University of Science and Technology, Polytechnics, Bucharest.
Hello, everybody. Actually, I'm not Daniela Faur. She couldn't come. So I'm the second author. My name is Corina Vodova. And today I will present on behalf of my colleagues of the Geoscience Lab from the University Polytechnic of Bucharest. A new approach to enhance Sentinel-2 data analysis. Large language retrieval augmented generation. So today I will first give you the context and the motivation for this research. I will introduce our approach, our innovation for this research, describe in detail each process, step of the process, present some preliminary experimental results, and then give some conclusion and talk about our future perspectives. Okay, so as you know, the climate change resulting in effects that are deeply embedded in all the environmental systems around us. So this demands for aggressive mitigation action. In order to protect all the communities and infrastructure that is around us, we need to identify which are the extreme events and try to manage and evaluate the associated risk that comes with these extreme events. One may say that with the unprecedented growth of Earth observation data, we have all the information that we need to give to take some actions that are well informed. However, this opens some paradox in the geospatial data analysis, because as we get our hands on a very detailed information of the Earth's surface, non-expert users, the common users, are very difficult to access due to the volume of information and complexity of those details that are encompassed in the geospatial data. Therefore, the need to implement the actual and operating tools to handle this geospatial data and to try to predict the risk associated with climate change is accelerating. Given this situation, our group was awarded with a national project where we have to build an integrated platform that must accommodate multiple sources of data and which are integrated continuously. Has to include to leverage artificial intelligence to give an assessment of risk associated with operations that happen in a very specific environment. So this project has a direct beneficiary, and this gives us very strict constraints for our project. The platform that we must build contains a robust self-contained AI methods that has to come with no online dependencies, must bring high interpretability, has to be real time, and has to give simple explanation in real language to a non-expert user, and handle all the direct interaction with the user through to text analysis. So this system must operate offline, must be deployed only in restrict environments because it's something, a use case related to national security, so it must be completely offline. It has to accommodate various various services, has to integrate multiple sources that are loaded by the user on the field, and must support information that is loaded directly on the field by the. So these are problems that can be easily addressed with large language models because they can cover this semantic gap between data and data, and the understanding of a human, which is not necessarily an expert in data processing. However, these language models, when they are operated in isolation, they face difficult challenges, like challenges referring to stability, to lack of domain-specific data, and also fine-tuning or retraining to cover this specific data requires extensive computation power. So I just switched to this. So can you hear me? In this framework, we introduce our approach is to try to leverage the capabilities of language models, but we combine them with an approach that is called retrieval augmented generation that can integrate external data and knowledge, semantic knowledge, data-specific, domain-specific knowledge extracted from external data and introduce it into the language models. First, we need to build that external data where we can define the domain knowledge information. Then we here leverage the capabilities of feature extraction, which can define the land cover, land uses of Earth that is helpful in various applications. Then we exploit the Facebook artificial information similarity search indexing model to try to make efficient also the data indexing and data searching into the process. With this indexing, we create a prompt engineering, which feeds the language models. In this process, we skip the part of the need for fine-tuning the language model. We speed up the process, the search, and we can easily replace at any time the language model in less than a minute without losing the actual information that is fed to the system. So our first step for the feature extraction, we don't just take the raw data, Sentinel Earth observation data. We extract physics-based information and use for start 6 spectral indexes describing spectral information on vegetation and soil, information that is very useful in various domain applications. So instead of 13 bands image, we have only 6 bands images, and this can be enlarged with other various features, texture or other information. For the database generation, as I said, we use the Facebook AI similarity search indexing method that is capable to handle dense vectors. Every data that is integrated into the database must be first divided into patches. For each patch, we compute the spectral indexes and aggregate this information with metadata or other semantic labels or other information that we can gather for that particular patch. And then they are stored in the database, which we call the Retrieval Augmented Generation Database. This is a RAG database. This is a very efficient process. For our specific case, it was done in less than 90 seconds using only a general computer, no specific computation power. So for our test, we first leveraged the database of Eurosat, contains 20,000 patches of Sentinel-2 data with no atmospheric corrections. This database includes 10 land cover classes, and the patch size is only 64 by 64 pixels. We selected this database because of the size of the patch. Each patch mostly contains a single class, or it's preponderantly covered by a single class. It not mixes several semantic classes, which you could confuse the model. So for initial test, we consider that this is a proper size. Just to mention that for this data set, Romanian areas were included in only 3% of the data set. As most of the models are developed for a single database and do not deliver good performances in other data sets, we built another data set using 2 different Sentinel images, nothing previously included in the Eurosat data. One is with atmospheric correction, the other one is without the atmospheric corrections, so different level of data processing. With this database, as I said, we want to test the applicability of and the performance of our approach in other data sets, to try to evaluate if the atmospheric corrections have any impact on the process, and also to try to see if the regional coverage is also a factor in describing using the language models. So if once we have the data sets, we just need to translate the numerical patterns that we extract, the spectral indexes, the semantic labels and everything. We must translate them into something that humans can easily read with no other knowledge. So we can apply large language models, and they can do this translation from numeric to language explanations. However, this analysis will miss the domain information. And in order to add context-aware and land cover description, we require large language models require fine-tuning. So this translates in the setting up billions of parameters and extensive computation resources, online dependencies, and so on. For our experiments, we used the Mistral model because it was the most efficient and the only open source language model developed in Europe. So our innovation is retrieval augmented generation, that entire framework with database and indexing. And this approach eliminates the need for fine-tuning. So we don't need to set up all these parameters. We have a pre-trained model. We feed into it that prompt engineering, some text that was creating using the indexed database. And the language models creates a response that has domain knowledge and can be obtained using only consumer-based computers, so no need for a large infrastructure. The process short is one must build the database, the reference with the spectral indices and the metadata. Then for the query, the user must do a click on the image, patch is extracted, spectral indexes are computed, is compared against the database. They are returned the most similar 5 patches, compare the information from those patches, the semantic information, put in a prompt, in a text, like a question, to the model, a language model, and that text is fed to the Mistral Nemo, which provides a description with more information about the actual context of the selected query. So for the first experiment, we initially eliminated for the database from the Eurosat data 5 patches per class. We assembled them into a synthetic image. As we said, we gave an example, just selected one patch. The prompt created looks like this. Like it identifies which spectral index was contained in that patch, or similar patches were retrieved. And here on the bottom, it says that this patch probably includes this kind of labels with that information. So the algorithm response provides this kind of analysis where it details the information about the spectral indexes included. And then explains the user what kind of combination of them and what does this mean for the content of the selected patch. For the 150 patches selecting a test data set, we got a high accuracy for the classes that cover almost the entire size of the patch. And the misclassifications, the errors for classification grow as the size of the class diminish. The time for the process is 7 seconds, so very fast. We repeated the process for the Sentinel-2 data. As the reference, we also use the Eurosat data. But for training, we only use the Sentinel-2 data. These are in preliminary, they are just in testing, preliminary results. The performance drop. Apparently, the atmospheric correction is not mitigating the errors. And the labeling confusions is we estimate that it can be caused by the by the lack of atmospheric correction in the Eurosat data, and also from the regional underrepresentation, because agricultural classes, let's say in Romania, might look different from agricultural classes in other regions. And to conclude, in a landscape where language models evolve very fast, we cannot build a platform that can be operative and remain the same performances. Therefore, we integrated in our platform this RAG method, as it preserves with the same external knowledge. That database allows the swapping of the language models into the platform. It's a process that takes less than a minute, and the classification is real time, like 7 seconds. It can run on every usual computer. So for the next step, we plan to enhance the spectral indexes or other features extracted from Sentinel-2, perhaps integrate some visual models and see what happens. Thank you for your attention, and if you have any questions, or feel free to contact.
Thank you very much for the presentation. Do we have any questions from the audience?
How are you deploying the large language model? Is it Llama or something like this?
We tested many models, but for this experiment, we stay with Mistral because...
No. But what is the runtime that you're running for it? Where are you running it? On Llama? What is the runtime for deploying the Mistral Nemo?
Few seconds.
The runtime, I mean the engine, the program that is running it.
Oh, okay. This is a question my colleague Theodore he was the one performing all the experiments.
Because this model specifically, it would need 3 of those GPUs, so you're probably reducing a lot of the quality of this model for it.
It's run online on some GPUs, a lot of infrastructure, but once the model is trained, he can be used on a usual computer.
Okay, thank you.
Any other question? Maybe one question on my side. The spectral information converted to LLM, like generated data, is there, like, are you collecting a data set for inferencing, or how is the generation happening? Because I assume there is a complex interaction for the generative process, right? When you're converting from the generation of each individual spectral indices, going from there to a remote sensing observation, there is a complex interaction of the spectral indices, right?
That's also a question for my colleague. Okay. But for each, when creating a database, they are computed on the spot. And for each patch, we retain only the mean of the spectral index. For NDVI, for instance, if we have a 64 by 64 patch, all those values are created on mean and saved into the database.
Okay.
And that is used further for search, comparing.
Sure. Thank you so much. Sure. Thank you.
So we'll be moving to the next speaker with Jeong et al. From Telepix in Korea. And he'll give a talk on SatChat, a multi-agent LLM-based service for enhanced observation and remote sensing.
Good afternoon. I'm Young-Sang Jeong, and head of the AI solutions team at Telepix and project lead for SatChat. Telepix is a startup based in South Korea, specializing in satellite development and related software solutions. So today's presentation topic is SatChat, multi-agent LLM-based service for enhanced Earth observation and remote sensing. We will first explore the big picture of how LLMs and agents are impacting Earth observation. Then I'll walk you through the architecture of the SatChat platform, our experimental results, and finally our future roadmap. Although satellite data and related solutions are rapidly growing, few lead directly to decision-making processes, and accessibility remains limited for non-experts. So from this perspective, we started with the question, what if anyone could easily ask natural language questions and instantly gain insights from satellite data? The exponential growth of EO data deepens the data divide. So analyzing just a single tip image involves several steps: understanding coordinate systems, defining AOI, and combinations, band combinations, and calling AI models, which makes it challenging for non-developers. So given this background, we determined the need to abstract complex EO workflows into an intuitive conversational interface. So why a multi-agent system instead of the single LLM? Recent studies such as MetaGPT and LLM Harmony report that role-based division of labor improves code quality by over 70% compared to single agent approaches. Since EO involves diverse tasks like image processing, orbit propagation, and document retrieval, we adopted the following structure: specialized agents running in parallel, dynamic role assignment, and automatic error correction through a reflection loop. Such a utilize a supervisor approach to efficiently coordinate multiple agents and tools to address user requests. LLMs and VLMs are actively used in remote sensing as well. On the left, remote sensing ChatGPT interprets user queries, plans tests, and generates responses. However, it lacks a dedicated user interface and only operates under predefined scenarios. And the right side showcases the research cases that utilize both natural language and images, but commercial services fully integrating domain knowledge and with multimodal reasoning remain rare. To overcome these limitations, we developed a SatChat, a multi-agent chatbot specialized in EO and remote sensing. So SatChat locates satellite imagery based on natural language queries, analyze it using AI, and provides additional context via external RAG. Users can interact via chat and maps, easily extending functionality by adding new agents and tools. SatChat offers 5 key differentiators. Users can easily search for satellite imagery and associated metadata using natural language, compute spectral indices like NDVI for specific regions, and visualize the real-time location of satellite on a map. And object detection and temporal change analysis are handled automatically using a YOLO-based model with the entire analytical process dynamically adapted to user prompts. To provide accurate and up-to-date responses, Sacha can leverage internet search engines and various public APIs. It also enhances its responses with scientifically grounded insights through retrieval augmented generation based on pre-indexed academic documents stored in a vector database. All of these features are integrated within a single chat interface and supported by intuitive map-based visualizations for enriched user experience. Such architecture comprises 3 stages: supervisor, execution, reflection. The supervisor agent analyzes user queries, creates a plan, and assign appropriate agents and tools. Domain execution agents handle tasks such as image processing and map visualization, while the knowledge agent provides credible references using vector database and web searches. The supervisor integrates results from each agent, completes the final response via reflection process, and reallocates tools as necessary. Let me illustrate this with a detailed real-world example. For instance, when a user asks the vehicle count within this boundary, the supervisor agent evaluates the user's question along with available context, such as satellite imagery data and the defined area of interest, to select the appropriate tools and agents. During this process, the supervisor agent plans optimal task distribution among agents, ensuring efficient execution through precise tool selection. The selected agents, such as image analysis, use the detect vehicle tool to detect vehicles within the specified AUI. Once the results are generated, the supervisor agent reviews them through the reflection process, ensuring they meet the user's requirements. So, if the response is inadequate or further analysis is required, the supervisor agent initiates the reprocessing or selects alternative tools to enhance the results. The final approved results are delivered to the user, optionally with visualization displayed on a map. For comprehensive evaluation, we built a data set consisting of 1,950 query context pairs, systemically categorized for G-eval. This data set was meticulously constructed to include 150 query context pairs for each of the 13 distinct tools supplied by SECHET, such as object detection, change detection, and spectral index calculations. The evaluation criteria comprised 3 key aspects: helpfulness, relevance, and faithfulness. And we adopted GPT-4o one of the latest LLM models to ensure highly reliable scoring. The ground truth was defined by assigning the corrector corresponding to each patterned user query. So we compared performance across different set versions powered by commercial LLMs and open source LLMs, aiming to clearly assess their practical applicability. Our experiments revealed that commercial GPT-4-based models demonstrate superior performance with GPT-4.1 mini exhibiting the highest accuracy in tool selection. Conversely, open source models generally showed significant performance but variability, particularly the smaller LLM models, which lacked consistency in their outputs. Although larger open source models displayed relatively stable performance, they still fell short of the commercial LLM benchmarks. These outcomes highlight the necessity for further optimization and technological enhancements to effectively operate multi-agent chatbots in an on-premise environment. Esa-Chat is a continually evolving project, and we are currently collaborating with institutions that require high security to develop on-premise chatbot solutions utilizing internal data. Based on recent experiments, we are modularizing agents and tools to improve efficiency in tool selection. We also plan to introducing advanced features such as time series analysis and mission planning. So additionally, we aim to personalize user experiment by analyzing interaction loss and refining user flow for diverse scenarios. Now, I'd like to show you a brief video demonstrating a real-world application of Esa-Chat. So this is very fast. Pay attention, please. So this concludes my presentation. Thank you for very much for listening. Yeah.
Any question? No. Okay, maybe I start. Okay, you present a use case whereby, okay, you count the number of cars or whatsoever. So how the system could be generalizable to any task. Like instead of counting cars, you can for swimming pool or whatsoever the use case without any prior knowledge of the use case. Because I guess for the cars or counting stuff, it's kind of already set up for this, right? So is the system truly, let's say, generalizable to any use case? Is the use case that you, is the system fully adaptable to any use case? Or is that working only for a set of limited use case that you show up here?
Okay.
Or different objects, different stuff to do on imagery, not only cutting cars or...
Yeah. That's it. But it was. You reach up them the line.
Sorry. So this is the ship detection.
Okay.
And we are adding another models to detect another objects. Yeah.
Okay, so you have to add each time some computer vision task model to learn it.
Yeah.
Oops.
I have one quick question before next topic. You mentioned planner. I was wondering if the planner is designed to handle long tail tasks where you have to chain one agent after another, where it forks into multiple tasks, and your response is contingent on multiple agents offhanding on their task to the next agent and contextualizing. The reason I'm asking is, can your planner handle that? And what kind of difficulties were you faced if you were thinking about designing planner that way?
Oh. That is good question, but I honestly haven't considered that. So this is my another challenge. Thank you.
Thank you. Yeah, thank you very much. The next presentation is about EVE, a suite of LLM and data for Earth observation and Earth sciences. The presenter is going to be Alex Ramirez Etrio and from PySchool. So let's get.
Hi everyone, I'm Alex. I'm from PySchool. It's a private research lab here in Rome. And I'm quite excited to be here today because it's the first time that we are presenting EVE in an event. Let me first introduce a bit the project high level, as well as the motivation, and then I'll go a bit more into some of the technical details. So EVE, fundamentally, it's a project to design a domain-specific LLM, as well as datasets for Earth observation and Earth sciences. We are releasing both a base as well as an instructed LLM that is trained on billions of high-quality Earth observation and Earth science data, and is capable of doing question answering on natural language, as well as summarization, as well as structured data extraction, so tables and things like that from raw text. This is integrated in a system with RAG and with a particular focus on scientific citations. And the target audience is both scientific audience for help regarding writing, reasoning, etc., as well as non-specialist users for dissemination of the technical knowledge. So, as I say, the main contributions are the domain-adapted as well as the instruction-tuned LLMs, the curated pre-training corpus, which is in the billions of tokens, the instruction and evaluation datasets in the Earth observation domain, manually created, the publicly accessible chat interface, which will be hosted by ESA-Lab, and the legal and compliance documentation, which for the data creation part is also quite important. This is a project where we're working with PySchool and Imperative Space, as well as ESA-Lab. And the project started last year and will end around November approximately, with a pilot phase that will happen probably around September, give or take. This is the rough pipeline of the project. So we are starting with an open weight LLM. We are gathering a very large amount of data of Earth observation. This is primarily scientific data. We are doing continued pre-training on the raw text. The domain adapted LLM, which is an artifact by itself, continues to be trained on instruction fine-tuning on a variety of downstream tasks like question answering, summarization, structured data extraction, etc. Then it's aligned on a dataset that we are creating manually for preference data for Earth observation. And then as far as the user is concerned, regarding the chat system itself, this aligned LLM is connected to a RAG database where the user can query it and get responses for those questions. So, as I say, the project right now is still ongoing. Most of the effort until now has been dedicated towards the data, but we're already working on an instructed Llama 318 billion, primarily on synthetic Earth observation data, focused on question answering and summarization. We already have the full 5 billion token clean processed Earth observation Earth science corpus, which will be released open source soon. And we are working right now on a RAG prototype with a small subset of this data. Right now, we are working on the manual annotation and creation of the Earth observation, IFT, and evaluation datasets that I was mentioning it, as well as starting the continued pre-training on the raw corpus, expanding the IFT that we are doing right now with broader high-quality data, so various subsets of question answering, reasoning, etc. And right now we're working with the 8 billion Llama, but we're scaling to a 20 to 70 billion architecture soon. Why do we do this and not just use ChatGPT? Well, if first of all is an entire suite, it's not just a model. So that means that, as I say, we are releasing the curated corpus as well as the instruction datasets, as well as the benchmarking evaluation datasets. We are also releasing the training and the RAG creation workflows, and the RAG itself, which is built on high-quality scientific database. And we are building a dedicated hallucination detection pipeline integrated into the RAG pipeline. Regarding the model itself, there is evidence that points that domain-specific LLMs, when properly done, can match generalist models on technical domains. Here you have some examples on similar domains. A comparatively small model means that it is more affordable for deployment and use. We are releasing it open weight, so the community can also do essentially whatever they want, quantize it, do further fine-tuning, etc. And finally, we are doing a manual evaluation on real Earth observation scenarios to demonstrate utility proper. Regarding data itself, right now, this is the table. So regarding the raw data, first row, we are working with 5.7 billion tokens open access data, which is the part that is going to be released curated. Then in addition, we have 1.1 billion tokens after an agreement with a major publisher, Wiley. That part will not be released, will be used for the continued training. We are also creating around 5,000 QA samples authentically on EO and Earth Science, as well as assembling summarization samples from articles authentically as well. And we are doing a variety of subformats of IFT synthetically, upwards of 1 million samples. We are also creating manually around 5,000 samples of EO preference data to do alignment. And the RAG database right now is expected to be around, to number around 300K articles. This 5.7 billion corpus we've created by manually identifying and scraping high-quality trusted sources. And we've developed a custom extraction and processing pipeline, and then we enrich the papers with the relevant metadata like journals, articles, year, etc. So more or less the token distribution looks like this. This is actually only the PDF subset, but it's representative. Most of it comes from peer-reviewed papers, MDPI, Copernicus, eGOOP, NCBI, etc. And some from generalist portals and things like that, like ESA, JAXA, NASA, and so on. Regarding the instruction fine-tuning, as I said, we have the 5,000 samples that we are creating right now, which we will use for both evaluation as well as grounding the synthetic generation. And this synthetic generation is going to be on multi-chunk document context. Regarding the model itself, the continuous pre-training is done on full precision using standard causal language modeling on the corpus described above. In addition to the Earth observation data itself, we are adding math and code because recently it has been shown to improve the reasoning abilities for downstream tasks. And we are performing annealing following the Llama 3.1 paper, which essentially just means that at the end of the CPT, we are doing a cyclical learning rate while upsampling a subset of the high-quality domain-relevant corpus. For the post-training itself, as I said, the instruction fine-tuning properly will be done on a variety of subformats of question answering, some open-ended, some multiple choice, some with, some without additional context. In addition, summarization. And finally, the structured data extraction from raw text. The alignment then will be done with the authentic preference EO dataset that we're creating. And then finally, we are going to do a model merging of the weights with a generalist LLM, which purpose is to mitigate the catastrophic forgetting that is inevitable when specializing the model on a given domain. Okay. Now, after the IFT proper regarding RAG, our main objective on RAG is to eliminate the factuality-based hallucinations. We are doing a fairly heavy continued pre-training on mainly science data, so this already decreases the chance of hallucination in both science and general domain. But on top of that, we have a framework that we develop, which consists first on flagging. So every model output, we run a mixture of uncertainty, which is just the internal LLM probability, and an external LLM as a judge. If the output is flagged as potentially having an hallucination, we reprompt with a chain of thought style prompting an external fact checker connected to RAG and trusted online sources. If it finds conflicting information, therefore, we first add this new information from the RAG database, meaning that the database is refreshed automatically. And then the if properly is reprompted with this new data and prompted to focus on the problematic span. This eventually we evaluate on the manual created EO dataset that we will release. So talking about evaluation, other than doing the evaluation on the standard general domain benchmarks to ensure that the overall capabilities of the model have not decreased too much after the specialization, we also do perplexity on selected text. This is for the base model. And for the Earth observation specific evaluation, we do evaluation on open-ended QA and multiple choice QA, on a hallucination/factuality dataset, and on a red teaming set, which is just a dataset of adversarial prompts with an expected answer and the actual answer. And as I say, all of these three datasets are being created manually and will be also released open source together with the models. And this is a very big overview of if. As I say, there is going to be a pilot phase around September probably. So you can register with the pilot for the pilot if you want on this QR code, or if you've seen in the poster room, there is also a roll-up kind of like this. You can also register there. And tomorrow in the morning, we will do a deep dive, explaining a little bit more some of the technical details, which Marcelo, a colleague, will do. And then in the afternoon, we will do a hands-on tutorial with a notebook explaining a little bit more in depth, which Antonio, another colleague, will do. So if you're interested, I urge you to also come. And that is it for me. Do you have some questions?
Okay.
Hi.
The instruction fine-tuning, you said about 5,000 questions. You doing them by hand?
Yes, with a mixture of things. So overall, it will be 5,000 human annotated, means some of them are going to be purely from scratch. And as you can imagine, obviously, the majority of them are going to be post-edited. So we do a synthetic generation, and then we have humans annotating them.
About using Llama 3.1 for your base model. The Llama license is problematic. Do you see any problem with that?
Yeah. I mean, the license itself is free in the sense we are able to do the open weights. What are you talking specifically about the release as open weights?
You cannot distribute it easily. You have to point that is made with meta.
Yes, that's it.
No, there is more than that. Yeah. Well, there is this thing with the number of users, but this.
Yeah.
You cannot put it for commercialization.
Yeah.
So, but right now there are better models, and that train faster. Okay, can fine tune faster than like Plan 3.
Yeah.
Or Mistral. Like someone said before.
Yeah. Right now, well, the two questions different. So first, regarding the compliant-wise constraints, indeed, the naming is really, as far as our use is concerned, is really the only main thing. Okay. We started experimenting on Llama also because it's a nice family to easily check scalability from 8 billion to 7 billion without any drastic changes to the architecture. It's quite likely that we're going to end up using probably some Mistral model, probably not Mistral Memo, but the 23 billion. So yeah, right now we're still working on the modeling part. So the choice on Llama family is not yet definitive, and it could very well end up being Mistral.
Okay, thank you.
Thank you so much for the presentation. One quick question with regards to your pre-training. So you did mention catastrophic forgetting, which would be one of the bottlenecks, I would say. But what are some other very practical issues that you faced? Some of the challenges, maybe top 2 or 3 that you could mention.
For the continuous pre-training specifically?
The pre-training specifically, in order not to lose performance compared to Llama itself.
Well, let me be clear on this because the project currently is still ongoing. So the continued pre-training we have not actually yet done. Now we did most of the data work, and now we're starting most of the benchmarking, the manual creation, and we're doing the post-training, let's say, the recipe, let's say. So in terms of empirical observations, I cannot yet say anything about what it means. Theoretically, obviously the main issue is going to be the catastrophic forgetting. But in principle, between a mixture of the instruction fine-tuning afterwards and the merging, we are expecting that we will be able to manage. Although inevitably there is going to be some loss on general capabilities. There's no free lunch in that sense.
Let's wait for a suggestion to that question, but can you do at the evaluation of this? I'd be interested to see, because you have a hallucination pipeline, a RAG with it, you do a comparison, be interested to see, you do an OpenAI model with a hallucination pipeline and RAG.
Yeah, I mean, thanks for the suggestion. And yeah, indeed, I mean, ultimately, the idea is, of course, that we are going to try to do a modular evaluation in the sense of, just the RAG and the hallucination with a different model, how it performs, as well as everything with different models. So yeah, indeed, we are going to do this, I think.
Good. There is a question in line. I understand.
Question online is, will Eve support image interpretation within papers?
Image interpretation? Regarding image, not directly images. Regarding things like formulas, code, tables, things like this, yes. In terms of pure images of like a map, for example, and things like this, it's currently not on the plan.
Sorry. It's getting late, but one more add-on. Will it support function calling for EO-specific APIs?
Okay. right now, it's not going to be one of the main objectives, I think, at least short-term, but it certainly would be nice to extend it to it.
Thank you.
Further questions?
But when I do planning to use reinforcement for fight unit that can work more efficiently and much better.
Yeah, it's quite likely that some part of the reasoning post-training we are going to use this. Yeah.
You know about which policy you're using?
No, not yet. Unfortunately, we are still not working on this yet, so we need to design it a bit more in detail.
Thank you so much.
Okay, thanks a lot.
Thanks very much.
Okay, next speaker is actually Kumar, and he will give a talk on AI-driven accelerated discovery for NASA Science Mission Directorate. Floor is yours.
Yep. Thank you so much. The actual presenter is not me. It is Kaylin Buckby, and I'm filling in for her.
Don't pay this. Go stay in the cup.
Thank you. So again, today's topic is about AI-driven accelerated discovery for NASA Science Mission Directorate. And originally supposed to be presented by Kaylin Buckby, but unfortunately, due to some travel reasons, she couldn't join us here today. But I'm gonna talk a little bit about like what her role is in NASA and what her focus is. So she's an applications data manager for NASA, and her work is on NASA is focusing on making NASA's data systems sustainable, resilient, and maintainable, while also enabling open science through transparency, reproducibility, and making our data open access within NASA Sciences. She also worked on maintaining and improving NASA science data holdings to ensure they are available for the scientists, not only today, but also in the future as well. So NASA's science data spans across 5 divisions, and that is astrophysics, biological and physical sciences, earth science, planetary, and heliophysics. So you can think of it spanning from the smallest of cells from the largest of galaxies. So you can think of there being a vast amount of variety and volume in terms of data here. And by the numbers, I'm going to give some FY23 numbers and some projections here. By FY23, we have some 10 million or so unique NASA science data users, 140 petabytes worth of data, and it's also growing at a rate of 50 petabytes per year in just rate. And so it's kind of projected to be around, to be greater than 500 petabytes, and it currently has around 1.5 billion total files as well. So really efficient data management is essential for NASA's mission here as well. One thing I need to make a point here is that due to this exponential increase of data and the large number of users and the varied expertise in these users, we need to make sure that it's easier for the scientists and other users to efficiently and effectively navigate through this vast amounts of data to make sure that their research can benefit from it. So that's where you can already kind of see where I'm going with this, and I'm going to spend the next few slides motivating why we use AI agents and LLMs, and our foundational principles and why and how we are going to use LLMs within NASA Sciences. So first and foremost, large language models can significantly cut down data discovery time. They can sift through multiple data discovery, access, literature review, and coding workflows. They can save off a significant chunk of time and reduce a lot of data wrangling overhead that scientists pose. And we are estimating around 80% or more in terms of removing the data wrangling time that is needed by using LLMs and AI effectively within the scientific data discovery and process, thereby we can enable scientists to directly analyze and interpret data rather than just the front-loading part of it. LLMs can also increase the visibility of data. They can make them easier to find, accessibility. They can increase the accessibility and break down barriers to use. They also allow more people to interact with data, so they add more value, increase the intrinsic value of that NASA data holdings that NASA has been collecting throughout the decades. So this is not just also enabling just existing data, existing processes faster, but they also can discover entirely new discovery pathways as well that the user has never discovered before because they lack the context that could be enabled by exploring other pathways as well. So LLMs can enable that as well. And they also enable easier or more contextual information retrieval, so it can enable user in different ways than they expected there as well. So they offer clear transformative benefits for data wrangling and exploration, and there's clear benefits to use them. But we need to do some clear alignment, and we need to align. It's paramount that we operate under a clear ethical framework because of some properties of LLMs here. We need to first and foremost prioritize open models, open data, open workflows, and code here. We also need to adhere to the principle of trust but verify. LLMs can clearly hallucinate and they can make up stuff. We all know that they can make up stuff, so we need to embrace this concept of verification always. We need to also formulate clear and concise questions. The more time we spend defining the problem more accurately, the better our answers can yield. And it can never be more true in the space of LLMs as well. We also need to, like I said, trust but verify process. We should never do unquestionable acceptance of AI-generated outputs as well. So that is, again, to quote Carl Sagan's baloney detection crit, we need to be always critically aware of the LLM outputs here. Another point is we need to approach we need to take the co-pilot analogy in approaching AI. We need to approach it as a collaborative partner, use AI as an aid in getting the output, but the responsibility, the accountabilities, and the integrity always lies central to the user, but not to the AI. So user accountability first approach, and AI is just another tool that will aid to get to the outcome in a much more rapid pace than ever before is the approach that we need to embrace here. So having laid those foundational principles here, we've been, ever since Bert2Ek and Bert Times, we've been exploring LLM space and exploring the ways in which we can contribute to LLMs for sciences. And we investigated whether NASA should build its own LLM for science and what it would mean for NASA to build LLM for science. Then if we decide to build our own LLM for science, what type of LLM? There are multiple types of LLMs. In modern LLM speak, we can build either encoder models or decoder models, and there is a middle ground that we can also build. And there are some implications that mean in choosing each of these pathways as well. So we need to choose carefully what all those implications means as well. And we also have models like Meta's Llama and other open models that like Quinn, like Alex mentioned. These also offer interesting checkpoints to latch off of and fine-tune further, and what that does mean for us as well. Then we also need to investigate curating pre-training materials and journal papers and technical reports to latch off of and to obtain the domain knowledge to build off of as well. So far, what we've done is partnered with IBM Research to build a LLM framework that involves curation of a large domain-specific corpora, We also developed a set of family of models. We call them Indus family of models that's tailored for various SMD applications that are currently operational. We also have a set of QA suites that evaluate these set of models on domain specificity and how good adapted to the NASA sciences domain specifically. We also, there is also a sentence transformer model, which we all know is essential in the retrieval augmented generation workflow, which is also available right now in Hugging Face. So some key takeaways from our previous exploration efforts is that collaboration were critical to some of the successes that were mentioned. A single type of model, at least in the encoder space, is not the right answer for all the solutions. So we needed to embrace a suite of models downstream, one downstream at a time, evaluate them and get them to deployment. And that was the approach that we took so far. And retrieval augmented generation for us is a cost-effective. We don't have to, since we already managed a wide range of data stewardship documents, so we didn't have to worry about generative process hallucinating incorrect responses because we relied on retrieval augmented generation and a wide swath of documents that we relied on for answering a user question. So that was a good middle ground for us. It has its own problems, but at that point it was a good middle ground for us. It also helped in automated content curation for some of the tools where it's easy to use content curation to put the mark certain documents to right kind of buckets. So it's easy for researchers to classify, consume the domain effectively using tools such as Science Discovery Engine. And we also have downstream that will be useful for some data stewardship workflows. One such example is Global Change Master Directory, which classifies a data set description to write keyword pair or set of keywords here, which will make a data discovery easier for scientists. If you know about Common Metadata Repository, CMR, it uses this mapping to initially populate a set of keywords for data sets. So we also have Indus used in search and retrieval, and again, sentence transformer and passage ranker has been used for indexing documents and re-ranking documents for a user query. And I think I'll skip this in the interest of time, and I'll talk a little bit more about the future direction, which is accelerated discovery. To briefly touch on this, we've gone from empirical observation where we focused on direct observation in the field of science, moving to theoretical models based on that, to simulating them using computers, and finding using data intensive science and using stochastic processes and Markov processes to enable science, and also then move to AML integration to do science. And then where we are going is to, or one branch of where we are going is to use AI and agentic systems using human collaboration. And we call it accelerated symbiotic discovery. So brief evolution of scientific paradigms here. A brief scientific discovery cycle here where we are trying to do here is use AI to automate parts of literature cycle, where it can help in identifying the hypothesis generation and formulate the experiments based on that. And those experiments will lead to data analysis, and those data analysis will lead to simulation and manuscript drafting and so on. So it's a cycle of literature leading to experiments, leading to results, leading to literatures and so on. And in the future, we could also see how this could be automated as well with human oversight. So with our foundational concepts in mind and where we are going towards in context, we are building a framework called accelerated discovery. a few core things that we need to keep keep in mind is we are maintaining like a agent repository where each agent is expert in a specific thing. We have nutrition illness search agent, data search agent. It's self-explanatory. But there is a planner agent, obviously, that can break down a research question and map it to a chain of research agents, which essentially forms an execution graph, which is a chain of these agents with a tightly coupled data interaction is what the outcome of this planning agent repository is. And obviously, human is the central point of the planner agent interaction. So, and for each agent, the main takeaway is that guardrail is an important component within each agent, and every input and output is rigorously checked for multiple layers of guardrails. And each tool here we can think of as an encapsulation to another agent as well. So essentially, in this framework, we are trying to prioritize a few things. You can think of observability here because human is in the loop. It's also modifiable by the human on how the things are chained together. They can change, hey, something doesn't look right, go back and redo it, and the planner should get that in context and rearrange the agents here. And it's also stateful and consistent because there is an execution graph that we can change the state of and things like that. There is also deeper guardrails as well. So I want to also show a video, if it can play, on a UI interaction of this agent. Can you play the video? So this is the UI. You can pose a question, which the question gets routed to the planner initially. Okay. So the planner initially creates a boilerplate template of agents. You can think of each of these boxes as agents. And once it creates a plan, then it then starts activating each agent, and then each agent is contextualized, parameterized. And we have explicit guardrails that are mentioned, which gets triggered based on the contents that's retrieved. We'll just let it run for some time. And the user should also be able to modify the state of any agent here by explicitly mentioning an agent and asking a question. And that should start a rewriting process here. The user was asking about changing the output format here, and that should rewrite the output to a different type of the different format. And that should essentially modify the state of the previous agent and change the state, because each of the agent is stateful here. Since we know the state of each agent, we can also show it in the UI itself. And we can also expand, see what the actual, see in a more detailed level what's happening. Should be able to change each individual aspects of it and rerun the state. So everything that's after that should have an effect of what's changed before that, and everything that's before that should not have an effect of what's changed after that, is the idea. Yep. So we can also repurpose each of these components to be closer to code. We are also envisioning on VS Code agent and have it closer to code down the line, but it's just a way we are thinking towards creating a framework that is extensible enough to have multiple ways of interaction. Concluding thoughts, integrate agentic AI foundation models and HPC infrastructure together and accelerate scientific discovery across scientific disciplines within NASA. And we want this to be open, transparent, and reproducible. We welcome thoughts, collaboration, and feedback on this effort. Yeah.
Basic. We have the time for one very short question. No.
Pass. Really like the output, being able to see it in the tree graph in terms of explainability. And I was thinking about doing a similar thing for a system I'm working on, but what I'm wondering is, like, do users really want to see that when they ask a question?
Yeah.
What?
There could be three kinds of users that we envision. So one kind of user won't really need ChatGPT kind of interaction. There's a second kind of user who want to be in control of the scientific process and want to export their work. Shareability is an important aspect within NASA Sciences. So this is specifically for the second kind of users. Then there is a third kind of users, which is the developers and the developer researcher who wants to work closer to the code, which is the VS Code user. So multiple users, and the second workflow enables the second type of user, where they have more control over what's happening, but not more lower level control. So it's a middle ground between the two, in a sense.
Thank you.
Thanks. We have to move to the next speaker. Thanks again.
Thank you.
So the next speaker will be online is Irene Pedura from ESA, and she will be giving a talk on the AI initiative from research to operation, AI AO data discovery assistant. And she will be actually online. And I guess she there. So the bus will wait for you. We did a certain margin, so we have to speed up. Well, yeah, stay here. This.
So, thank you everyone. Apologies for not being able to be there in person. Today I would like to present an AI initiative from research to operations. My name is Hayat Abdullah Kiri, and I'm working in the EOPGE section, which is common services and deals with the dissemination of data for Earth Explorer and third-party missions. So just to give you a bit of context, we're working facilitating data access for approximately 80 ESA and third-party missions, which amounts to approximately 205 data collections and 40 million, which are broken down to 40 million data products. Our target users are scientists, researchers, and professionals across various domains who are interested in using the data. These users possess expertise in their own scientific fields, but are typically unfamiliar with the services provided by ESA's ground segment. So for these users, we wanted to start introducing AI into some of our systems. So in 2023, we had the idea to start a demonstrator activity for an EO AI technical support assistant. We have quite a few websites, which amount to about 3,700 web pages and 4,700 documents. And we also have a database from our ticketing system, which has about 52,000 tickets from users with queries. And we wanted to see if, by using large language models and retrieval augmented generation, we could enhance the user experience for our users, demonstrate the usage of more innovative solutions, and meet the changing user needs. We wanted to see how we could integrate LLMs into our operational workflows, perform data anonymization, because obviously the tell us tickets would have had personal information in them. And we wanted to understand how an LLM would perform with something like sentiment analysis and classification of our tell us tickets. So the workflow for the project, and this was a project that lasted approximately 9 months, was to extract, obviously, all the technical documentation from the ESA websites and the web contents and generate embeddings, which were stored in an OpenSearch database. Then we had, obviously, our 52K tickets from our TELUS database. These were anonymized by using an LLM, also combined with regular expressions and rules, where we achieved actually quite a good anonymization rate of about 98.9, which is comparable with the human anonymization rate. So if an operator were to do it, which would be about 99.3. And then the data was put through a sentiment analysis step. We used the Twitter-based Roberta model, which was trained on 124 million tweets. And we generated 3 sentiment classes, where we found that 93% of our users were provided positive or neutral feelings, so no significant emotional charge for the neutral feelings for the tickets that were analyzed. And these were then further classified and stored within the OpenSearch database. There was also a GUI designed, and obviously users could interact with the large language model through the GUI. A similarity search was performed in the database to extract the relevant information that was stored, and this was fed into the LLM, and the results were provided to the user, so the answers to their query. So these would be queries like what was the launch date of the Swarm mission, for example, or what are the most important features of the CRIS instrument, something like that, which would be an instrument on one of the satellites. The initial results of the study were promising, and the answers from the LLM were actually very good, and we found that hallucinations were actually quite reduced by having reliable information provided from the websites, because obviously all of our information is rigorously checked. However, we found that the format of a lot of the information could have been improved. The kind of FAQ style information seemed to do better than our standard, obviously, just general texts, which were not obviously used for or developed or written for these purposes. So there was a little bit of work to be done, but overall it was an interesting study. Following on from that, in 2024, we wanted to see how we could use AI for data discovery. So as I mentioned earlier, we have a catalog of 40 million data products, 200 collections, and we wanted a simplified process for the discovery of this data. So for users to actually query a database and actually be suggested relevant information, to lower the barrier for entry-level users with limited knowledge of Earth observation terminology and ESA missions, which they might not know off the bat. And we wanted to provide consolidated EO product proposals based on user queries and their data requirements, including spatial and temporal requirements. So for example, if they're looking for data over a specific area of the globe and during a specific time range. So the innovations here were just obviously leveraging the capabilities of large language models, comprehensive data utilization, so ensuring that we used all of the collections which had various data access conditions and mechanism, and we wanted the requirement-based recommendations, which I mentioned earlier, using the temporal and spatial parameters. So here I'm just going to quickly take you through the pipeline of the EO AI data discovery assistant, which was also a demonstrator project. So again, it wasn't scaled, it was just to see the feasibility. So an end user would obviously have to go through a user authentication and login step in order to sign in, whereby they would access their user profile, and there they would have, for example, their history, their conversation history stored. They would interact with a large language model, so they would pass their query, which would go through a correction and validation mechanism. So the idea behind that is that we would use an EO-trained Roberta transformer model, which was used to obviously reduce hallucination and to validate the data and to ensure that the parameters aligned with the API requirements. The query would then go to a query processing stage where there would be query decomposition. So basically understanding if it's a single or multi-API call to our catalog, and to understand also the number of parameters. The query would be broken down into embeddings to understand the user intent, and also a geodecoding step would be applied where location information would be converted into bounding boxes. In the collection retriever, then there would be a hybrid search performed, so both a semantic and keyword search. The idea behind the semantic search was to query a vector database with collection information in order to retrieve the relevant descriptions for the collection for that particular query. And then in addition, the collection IDs, which would be used in order to put together the EOCAT API call. From the API call, you would be able to then retrieve an image, so a quick look of the data, of the relevant data products, a bounding box for the product visualization, a link to where to download the data products file, and an interactive product map which would be generated. These would be then passed back to the large language model, which would prepare a response for the user. So overall, this project was very successful, and it showed that data discovery can also be simplified for a lot of users who are unfamiliar with which data they need and might only know, for example, the thematic area that they're interested in, something like agriculture or, I don't know, sea ice temp or sea surface temperature, things like that. So this year we decided that it would be interesting to go a little further, and we wanted to combine the results that we had in our previous two demonstrators, so our EOAI Technical Support Assistant and our Data Discovery Assistant, into an EOAI Advanced Assistant, which would be, let's say, a more consolidated beta version, closer to, let's say, an operational model, which we are hoping to deploy later on this year. So what was the idea behind the EOAI Advanced Assistant? So firstly, to simplify access to data and services for entry-level and experienced users. These services would include automated user support. So for example, allowing users to more easily discover and open tickets for support or for requesting data from our operators. Providing data product suggestions, which would be covered by our Data Discovery Assistant, but also, for example, providing simple data visualizations, which would be something that would be in addition to what was done in the Discovery Assistant. Providing technical resources, which was done via the Technical Support Assistant, and also some additional support for developers in integrating EO data into applications. So this would be an additional step on the technical support assistant, and then ensuring a flexible and scalable architecture that serves as a foundation for integrating future AI-driven tools. So we wanted a multi-agent solution. It seemed like the most natural next step, and deliver and deploy a beta version. So we wanted to hybridly integrate complex generative AI workflows, comprehensively utilize the data metadata, have the requirement-based data recommendations as previously, and real-time and interactive data visualizations based on natural language. So just to give you an idea of the high-level architecture of the project, which has kicked off in April, so it's quite new. We would have a user interface which would interact with an AI agent orchestrator. This orchestrator would then interact with the data discovery and visualization assistant. So the data discovery part I described earlier in the pipeline, and the visualization would be in addition to that, and I will go into that a bit later. The technical support assistant with the addition of a development support assistant, and then a new element would be a ticketing assistant. We would also have obviously a personalization database to ensure user authentication and, for example, things like real suggestions for users or more personalized suggestions. As well as remember things like conversation history. And then a general purpose LLM. And here we're testing a few LLMs at the moment. Initially, we started with Llama, but we're also looking at other models that are coming up at the moment. Sorry, just a second. I think I just received a message. Just wanted to see what it was. Okay, no worries. For the AI agent orchestrator, the main aims are to allow the query to be routed to the correct subsystem for processing, to allow subsystems to exchange information. We wanted to also ensure that we could add further tools in the future to expand the system, and we wanted that the AI orchestrator will obviously aggregate the outputs from the various systems into a coherent reply to the user. For the data discovery assistant, so I won't go into the details. Obviously, it's similar to what was developed previously. However, here we would like to assess an integration with an additional contract that we have, which is called Ascend. Here, there is a provision of new data sources with extended visualization capabilities. So, for example, pixel-based data. So we would actually be able to visualize real data on the map rather than quick looks. And here, just to give you an example, what we had done in the data discovery assistant is that you could see a bounding box, and when you clicked on the bounding box, you'd be able to see the start date and end date of an acquisition, the instrument name, the sensor type, a link to download the individual data, and then a quick look. And what we want to achieve is to actually visualize the data within the browser while the conversation is happening with the user. Then for the technical support assistant, the added element would be the development support assistant. Here, it would be important to, for example, provide coding snippets and to allow the user to seamlessly integrate the API into their own code. So just to give you an idea, the AI technical support assistant would give you answers such as how do I access Cryostat data, but we wanted to provide something a bit more detailed, like can you give me the Python code for querying the AI catalog? Sorry. Okay, sorry. I'll close now. Just the ticketing assistant then would allow for the summarization for opening requests, for requesting, for example, restrained data. And personalization database would allow for integration with our UIM system and providing personalized recommendations, additional similar collections, for example. For operations, we want to look obviously at scalability by supporting an increasing number of parallel users. So at the moment, we're looking at 10 parallel users, but we need to understand what are the limitations with hardware in doing that. We want to obviously monitor our system and components. We want to benchmark the system. We want compliance with data protection and compliance with security rules. And here we want to look at trustworthiness, for example, as an additional property, in addition to the traditional ones for security. And finally, I just want to say there's quite some work left before the launch of the full assistant. The AI landscape is changing quickly, so we need some adaptation. We want some gradual scaling to preserve resources, and we want to meet user expectations with new and innovative tools. Thank you. Don't know if you have any questions.
Thank you so much, Tula. We will have the questions online in the chat, sorry, in the interest of time, but the next presenter is going to be Alexandra, and the topic is Labrador, and the Jülich Super, and it's from the Jülich Super Computing Center. Alex, I would request if you can 2x.
If you can do what?
If you can double your speed of your presentation. Sorry about that.
Okay. I'm Alex, not the other bald Alex. And I will try to be quick. I will not put numbers because it's boring. We are all tired. We all want to leave and we are very late. Yeah? So what is Blalador? Blalador, imagine a ChatGPT, which is for free, which is private. That's it. We can go home. This is the QR code of it. So this is a server that we have in Jülich that is running for 2 years now. We are doing a chat bot. And people have been using it, and we have an API server, and people have been building on top of it. I'll put more pictures of dogs because really we had enough here. Yeah. This is the slides. If you want the slides, just take a picture. If not, you can get it later. Oh, okay. Someone is scanning.
We're gonna do.
All right. Thank you. If you want to enter the website, you need a Google account or a GitHub account or an OrcID account. That's it, or either or. Yeah. What is it? As I said, well, look, I will not go much. And so blah, blah, blah is a blah, 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 because those things hallucinate and they bullshit a lot. And when I was running this 2 years ago, it was way worse than it is now. So it was a place for us to test those large language models. Yeah, so we were putting new models every time now and then. We keep changing the models. Now we're getting more hardware, so we can put more models. The models are better. So it's the website, it's an API server, and running models. Yeah. So okay, there is this is Internet Explorer. I'm sorry, but that was a dog. This is how it looks like. I mean, you have seen a million of those, right? It's the same. The thing is that we are running it local, and I don't log absolutely anything, in the sense that people that are doing confidential stuff, they can use it. Yeah, it's being used by project managers, by people developing patents and things like this. And we did it because people in Jülich were doing like half of the conference today. Oh, we developed this model. Okay, fine. And then so what? Where do you run it? Where do you deploy it? Oh, no, it's on GitHub. Oh, look. What do I do with a GitHub? Now you need a hardware for that. Yeah. So what I did was to take to get ready for those models that were being produced in Jülich, large language models. And when they finish their models, we are good and we can deploy them right away. That's it. I think I can, and I did it because I could, to be honest. So yeah, more dogs. This is the original blah, blah, blah. Yeah, and so we have those two projects in Jülich called OpenGPTX and TrustLLM. They are LLMs. They think about the training, but never thought about where they would put these things to run when they are finished. So I said, okay, then I'll do it. Yeah, so I did it because I could. And again, privacy, that's very easy to do in the sense that you just don't record anything and then you're GDPR compliant. That was perfect. Yeah. Yeah, and then this is blah, blah, blah. Yeah, there is an API, so you can build your agents on top of our models. Doesn't matter. And so this is old. We are here now. We have like 1,000 users a day, which is nice, and we have 1,500 users on the web, on the API. Sorry. Yeah, and this started as a side project for me. So it was a small cluster that I made a copy of the supercomputer. It was this with gaming GPUs. Yeah, so this is me fixing, like doing full stack development. Yeah, like literally from touching the hardware all the way to the UI. Now we're getting an AI factory in Jülich, and basically the deployment is not just about large language models, but all the inference of science models and simulation-based inference in Jülich. So we are getting more stuff. So right now we have, so those are some boring models. So for example, this one is running Blalador now, one of those. And I'll get a whole row like this until the end of the year to run large language models plus other kinds of models like the models that you are generating. Yeah. This was an architecture of the thing. It doesn't matter. It's a bunch of modules. Okay, the rendering is all wrong because of the font. But it's a classic website with an API server, with a runner for the models, models running on a supercomputer, models running directly, and that's it. And I think we are done.
That's
Yeah. I have stickers. If you like stickers for your laptop, I have little stickers with the logo like this. It's like a dog and like a chat bubble. Yeah. So, yeah. Thank you.
very good.
Well, I guess we don't have any time for questions.
Let's go and we talk.
And yes, thanks.
We know this. Yeah, correct.